Yolov8, one of the most powerful computer vision technologies ever made. In this video, I'm going to show you how to do object detection, image classification, image segmentation, and pose detection on your own custom data using Yolov8. I'm going to show you the entire process, how to annotate your data, how to do the training, how to analyze the performance of the model you trained, and how to use the model to make predictions. This is a full, comprehensive tutorial on Yolov8, and now let's get started. Hey, my name is Felipe and welcome to my channel. In this video we are going to train an object detector using Yolov8, and I am going to walk you step by step through the entire process, from how to collect the data you need in order to train an object detector, how to annotate the data using a computer vision annotation tool, how to structure the data into the exact format you need in order to use Yolov8, how to do the training, and I'm going to show you 2 different ways to do it, from your local environment and also from a Google Colab, and how to test the performance of the model you trained. So this is going to be a super comprehensive step-by-step guide of everything you need to know in order to train an object detector using Yolov8 on your own custom dataset. So let's get started. So let's start with today's tutorial, let's start with this process, and the first thing we need to do is to collect data. The data collection is the first step in this process. Remember that if you want to train an object detector or any type of machine learning model, you definitely need data. The algorithm, the specific algorithm you're going to use, in this case Yolov8, is very important, but the data is as important as the algorithm. If you don't have data, you cannot train any machine learning model. That's very important. So let me show you the data I am going to use in this process. These are some images I have downloaded and which I'm going to use in order to train this object detector, and let me show you a few of them. These are some images of alpacas. This is an alpaca dataset I have downloaded for today's tutorial, and you can see these are all images containing alpacas in different postures and in different situations, right? So this is exactly the data I am going to use in this process, but obviously you could use whatever dataset you want. You could use exactly the same dataset I am going to use, or you can just collect the data yourself. You could just take your cell phone or your camera or whatever, and you can just take the pictures, the photos, the images you are going to use. You can just do your own data collection. Or something else you could do is to just use a publicly available dataset. So let me show you this dataset. This is the Open Images dataset version 7, and this is a dataset which is publicly available, and you can definitely use it in order to work on today's tutorial, in order to train the object detector we are going to train on today's tutorial. So let me show you how it looks like. If I go to Explore and I select Detection, you can see that I'm going to unselect all these options. You can see that this is a huge dataset containing many categories. I don't know how many, but there are many. This is a huge dataset. It contains millions of images, hundreds of thousands, if not millions of annotations, thousands of categories. This is a super huge dataset, and you can see that you have many different categories. Now we are looking at trumpet, and you can see these are different images with trumpets, and from each one of these images we have a bounding box around the trumpet. And if I show you another one, for example, we also have beetle. And in this category, you can see we have many different images from many different type of beetles. So this is another example. Or if I show you this one, which is bottle, and we have many different images containing bottles. For example, there you can see many different type of bottles, and in all cases we have a bounding box around the bottle. And I could show you, I don't know how many examples, because there are many different categories. So remember, the first step in this process is the data collection. This is the data I am going to use in this project, which is a dataset of alpacas, and you can use the exact same data I am using. If you want to, you can use the same dataset of alpacas, or you can just collect your own dataset by using your cell phone, your camera, or something like that. Or you can also download the images from a publicly available dataset, for example, Open Images dataset version 7. If you decide to use Open Images dataset version 7, let me show you another category, which is alpaca. This is exactly from where I have downloaded all of the images of alpacas. So if in case you decide to use this publicly available dataset, I can provide you with a couple of scripts I have used in order to download all this data and in order to parse through all the different annotations and to format this data in the exact format we need in order to work on today's tutorial. So in case you decide to use OpenImages dataset, I am going to give you a couple of scripts which are going to be super useful for you. So that's all I can say about the data collection. Remember, you need to collect data if you want to train an object detector, and you have all those different ways to do it, and all these different categories and all these different options. So now let's move on to the next step. And now let's continue with the data annotation. You have collected a lot of images, as I have over here. You have a lot of images which you have collected yourself, or maybe you have downloaded this data from a publicly available dataset, and now it's the time to annotate this dataset. Maybe you were lucky enough when you were creating the dataset, and maybe this dataset you are using is already annotated. Maybe you already have all the bounding boxes from all of your objects, from all your categories. Maybe that's the case, so you don't really need to annotate your data. But in any other case, for example, if you were using a custom dataset, a dataset you have collected yourself with your own cell phone, your camera, and so on, something you have collected, in that case you definitely need to annotate your data. So in order to make this process more comprehensive and in order to show you like the entire process, let me show you as well how to annotate data. So we are going to use this tool, which is CBAT. This is a labeling tool. I have used it many times in many projects. I would say it's one of my favorite tools. I have used pretty much absolutely all the object detection, computer vision related annotation tools I have used. Maybe I haven't used them all, but I have used many of them. And if you are familiar with annotation tools, you would know that there are many of them, and none of them is perfect. I will say all of the different annotation tools have their advantages and their disadvantages, and for some situations you prefer to use one of them, and for other situations it's better to use another one. CBAT has many advantages and it also has a few disadvantages. I'm not saying it's perfect, but nevertheless this is a tool I have used in many projects and I really like it. So let me show you how to use it. You have to go to cbat.ai and then you select try for free. There are different pricing options, but if you are going to work on your own or in a very small team, you can definitely use the free version. So I have already logged in. This is already logged into my account, but if you don't have an account, then you will have to create a new one. And yeah, so you're going to see like a sign up page, and you can just create a new account, and then you can just log into that account. So once you are logged into this annotation tool, you need to go to projects and then create a new one. I'm going to create a project which is called Alpaca Detector, because this is a project I am going to be working in, and I'm going to add a label, which in my case is going to be only one label, which is alpaca, and then that's pretty much all. Submit and open. I have created the project. It has one label, which is alpaca. Remember, if your project has many different labels, add all the labels you need. And then I will go here, which is create a new task. I am going to create a new annotation task, and I'm going to call this task something like alpaca detector annotation task 001. This is from the project Alpaca Detector, and this will take all the labels from that project. Now you need to upload all the images you are going to annotate. So in my case, I'm obviously not going to annotate all the images, because you can see these are too many images and it doesn't make any sense to annotate all these images in this video. These are 452 images, so I'm not going to annotate them all, but I'm going to select a few in order to show you how exactly this annotation tool works and how exactly you can use it in your project. Also, in my case, as I have downloaded these images from a publicly available dataset, from the Open Images dataset version 7, I already have the annotations, I already have all the bounding boxes. So in my case, I don't really need to annotate this data because I already have the annotations, but I'm going to pretend I don't, so I can just label a few images and I can show you how it works. So now I go back here and I'm just going to select something like these many images, right? Yeah, I'm just going to select these many images. I'm going to open these images and then I'm going to click on submit and open, right? So this is going to create this task and at the same time it's going to open this task so we can start working on our annotation process. Okay, so this is the task I have just created. I'm going to click here in job number and the job number, and this will open all the images, and now I'm going to start annotating all these images. So we are working on an object detection problem, so we are going to annotate bounding boxes. We need to go here and, for example, if we will be detecting many different categories, we will select what's the category we are going to label now, and that's it. In my case, I'm going to label always the same category, which is alpaca, so I don't really need to do anything here. So I'm going to select shape, and let me show you how I do it. I'm going to click in the upper left corner and then in the bottom right corner. So the idea is to enclose the object and only the object, right? The idea is to draw a bounding box around the object and anywhere else, right? You only want to enclose this object. And you can see that we have other animals in the back, right? We have other alpacas, so I'm just going to label them too. And there is a shortcut which is pressing the letter N, and you can just create a new bounding box. So that's another one, this is another one, this is another alpaca, and this is the last one. Okay. That's pretty much all. So once you're ready, you can just press Ctrl S. That's going to save the annotations. I recommend you to press Ctrl S as often as possible because it's always a good practice. So now everything is saved. I can just continue to the next image. Now I'm going to annotate this alpaca, and I'm going to do exactly the same process. I can start here, obviously. You can just start in whatever corner you want. And I'm going to do something like this. Okay, this image is completely annotated, and I'm going to continue to the next image. In this case, I'm going to annotate this alpaca too. This is not a real alpaca, but I want my object detector to be able to detect this type of objects too. So I'm going to annotate it as well. This is going to be a very good exercise because if you want to work as a machine learning engineer or as a computer vision engineer, annotating data is something you have to do very often, or actually training machine learning models is something you have to do very often. So usually the data annotation is done by other people, right? It's done by annotators, it's done by, I don't know, there are different services you can hire in order to annotate data. But in whatever case, whatever service you use, it's always a very good practice to annotate some of the images yourself, right? Because if you annotate some of the images yourself, you are going to be more familiar with the data, and you're also going to be more familiar on how to instruct the annotators on how to annotate this particular data. For example, in this case, it's not really challenging. We just have to annotate these two objects, but let me show you. There will be other cases because there will be always situations which are a little confusing. In this case, it's not confusing either. I have just to label that object. But for example, a few images ago when we were annotating this image, if an annotator is working on this image, it's that person is going to ask you, what do I do here? Should I annotate this image or not? Right? If an annotator is working on this image and the instructions you provide, they are not clear enough, this person is going to ask you, hey, what do I do here? Should I annotate this image or not? Is this an alpaca or not? So, for example, that's a situation. Another situation would be what happened here, which we had many different alpacas in the background, and some of them, for example, this one is a little occluded. So there could be an annotator, someone who asks you, hey, do you want me to annotate absolutely every single alpaca, or maybe I can just draw a huge bounding box here in the background and just say everything in the background is an alpaca. Something like that. When an annotator is working on the images, they are going to have many different questions regarding how to annotate the data, and they are all perfect questions and very good questions, because this is exactly what's about. I mean, when you are annotating data, you are defining exactly what are the objects you are going to detect, right? So what I'm going is that if you annotate some of the images yourself, you are going to be more familiar on what are all the different situations, on what exactly is going on with your data. So you are more clear in exactly what are the objects you want to detect, right? So let's continue. This is only to show a few examples. This is another situation. In my case, I want to say that both of them are alpacas. So I'm just going to say something like this. But there could be another person who says, no, this is only one annotation, it's something like this, right? I'm just going to draw one bounding box enclosing both of them, something like that. And it will be a good criteria. I mean, it will be a criteria, which I guess it will be fine. But whatever your criteria would be, you need one, right? You need a criteria. So while you are annotating some of the images, is that you are going to further understand what exactly is an alpaca, what exactly is the object you want to consider as alpaca. So I'm just going to continue. This is another case which may not be clear, but I'm just going to say this is an alpaca, this black one, which we can only see this part and we don't really see the head, but I'm going to see it. I'm going to say it's an alpaca anyway. This one too, this one too, this one too. Also, this is something that always happens to me when I am working, when I am annotating images, that I am more aware of all the diversity of all these images. For example, this is a perfect example, because we have an alpaca which is being reflected on a mirror, and it's only like a very small section of the alpaca. It's only like a very small piece of the alpaca's face. So what do we do here? I am going to annotate this one too, because yeah, that's my criteria. But another person could say, no, this is not the object I want to detect. This is only the object I want to detect. And maybe another person will say, no, this is not an alpaca. Alpacas don't really apply makeup on them. This is not real, so I'm not going to annotate this image. You get the idea, right? There could be many different situations, and the only way you get familiar with all the different types of situations is if you annotate some images yourself. So now let's continue. In my case, I'm going to do something like this, because yeah, I will say the most important object is this one, and the other ones are like, yeah, it's not really that important if we detect them or not. Okay, so let's continue. This is very similar to another image. I don't know how many I have selected, but I think we have only a few left. I don't know if these type of animals, they are like natural. I'm very surprised about this, like the head, right? It's like it has a lot of hair over here, and then it's completely hairless, the entire body. I mean, I don't know, I'm surprised. Maybe they are made like that, or maybe it's like a natural alpaca. Who cares? Let's continue. So we have, let's see how many. We have only a few left, so let's continue. Let's see if we find any other strange situation which we have to define if that's an alpaca or not, so I can show you an additional example. Also, when you are annotating, you could define your bounding box in many different ways. For example, in this case, we could define it like this. We could define it like this. I mean, we could define it super fit to the object, something like this. Super fit, and we could enclose exactly the object, or we could be a little more relaxed, right? For example, something like this will be okay too, and if we want to do it like this, it will be okay too, right? You don't have to be super accurate. You could be like a little more relaxed, and it's going to work anyway. Now in this last one, and that's pretty much all. This is the last one. Okay. I'm going to do something like this. No, I'm going to do it like this. I think this is also alpaca, but anyway, I'm just going to annotate this part. So that's pretty much all. I'm going to save. And those are the few images I have selected in order to show you how to use this annotation tool. So that's pretty much all for the data annotation. And remember, this is also a very important step. This is a very important task in this process, because if we want to train an object detector, we need data and we need annotated data. So this is a very important part in this process. Remember this tool, CBAT. This is only one of the many available image annotation tools. You can definitely use another one if you want. It's perfectly fine. It's not like you have to use this one at all. You can use whatever annotation tool you want. But this is a tool I think it's very easy to use. I like the fact it's very easy to use. It's also a web application, so you don't really need to download anything to your computer. You can just go ahead and use it from the web. That's also one of its advantages. So yeah, so this is the tool I show you in this video how to use in order to train this object detector. So this is going to be all for this step, and now let's continue with the next part in this process. And now that we have collected and annotated all of our data, now it comes the time to format this data, to structure this data into the format we need in order to train an object detector using Yolov8. When you're working in machine learning and you're training a machine learning model, every single algorithm you work with, it's going to have its own requirements on how to input the data. That's going to happen with absolutely every single algorithm you will work with. It's going to happen with YOLO, with all the different YOLO versions, and it's going to happen with absolutely every single algorithm you are working with. So specifically, Yolov8 needs the data in a very specific format. So I created this step in this process so we can just take all the data we have generated, all the images and all the annotations, and we can convert all these images into the format we need in order to input this data into Yolov8. So let me show you exactly how we are going to do that. If you have annotated the data using CBAT, you have to go to Tasks, and then you have to select this option, and it's Export Task Dataset. It's going to ask you the export format, so you can export this data into many different formats, and you're going to scroll all the way down, and you're going to choose YOLO 1.1, right? Then you can also save the images, but in this case it's not really needed. We don't really need the images, we already have the images, and you're just going to click OK. Now, if you wait a few seconds or a few minutes, if you have a very large dataset, you're going to download a file like this, and if I open this file, you're going to see all these different files, right? You can see we have 4 different files, or actually 3 files and a directory, and if I open the directory, this is what you are going to see, which is many different file names. And if I go back to the images directory, you will see that all these images file names, they all look pretty much the same, right? You can see that the file name, the structure for this file name looks pretty much the same as the ones we have just downloaded from CBAT. So basically the way it works is that when you are downloading this data into this format, into the YOLO format, every single annotation file is going to be downloaded with the same name as the image you have annotated, but with a different extension. So if you had an image which was called something.jpg, then the annotation file for that specific image will be something.txt, right? So that's the way it works. And if I open this image, you are going to see something like this. You're going to see, in this case, only one row, but let me show you another one which contains more than one annotation. I remember there were many, for example, this one, which contains 2 different rows, and each one of these rows is a different object. In my case, as I only have alpacas in this dataset, each one of these rows is a different alpaca, and this is how you can make sense of this information. The first character is the class you are detecting. I wanted to enlarge the entire file, and I don't know what I'm doing. There, okay. Okay, The first number is the class you are detecting. In my case, I only have one, so it's only a 0 because it's my only class. And then these 4 numbers which define the bounding box, right? This is encoded in the YOLO format, which means that the first 2 numbers are the position of the center of the bounding box. Then you have the width of your bounding box and then the height of your bounding box. This, you will notice, these are all float numbers. And this basically means that it's relative to the entire size of the image. So these are the annotations we have downloaded, and this is in the exact same format we need in order to train this object detector. So remember, when I was downloading these annotations, we noticed there were many different options. All of these different options are different formats in which we could save the annotations. And this is very important because you definitely need to download YOLO, because we are going to work with YOLO, and everything is pretty much ready as we need it in order to input into Yolov8, right? If you select YOLO, that's exactly the same format you need in order to continue with the next steps. And if you have your data into a different format, maybe if you have already collected and annotated your data and you have your data in whatever other format, please remember you will need to convert these images, or actually to convert these annotations into the YOLO format. Now, this is one of the things we need for the data. This is one of the things we need in order to, we need to format in order to structure the data in a way we can use this object detector with Yolov8. But another thing we should do is to create very specific directories containing this data, right? We are going to need 2 directories. One of them should be called images and the other one should be called labels. You definitely need to input these names. You cannot choose whatever name you want. You need to choose these 2 names, right? The images should be located in a directory called images, and the labels should be located in a directory called labels. That's the way Yolov8 works. So you need to create these 2 directories. Within your images directory is where we are going to have your images. If I click here, you can see that these are all my images. They are all within the images directory. They are all within the train directory, which is within the images directory. This directory is not absolutely needed, right? You could perfectly take all your images, all these images, and you could just paste all your images here, right in the images directory, and everything will be just fine. But if you want, you could do something exactly as I did over here, and you could have an additional directory which is in between images and your data and your images, and you can call this whatever way you want. This is a very good strategy in case you want to have, for example, a train directory containing all the training images, and then another directory which could be called validation, for example, and this is where you are going to have many images in order to validate your process, your training process, your algorithm. And you could do the same with an additional directory which could be called test, for example. Or you can just use these directories in order to label the data, right? To create different versions of your data, which is another thing which is very commonly done. So you could create many directories for many different purposes, and that will be perfectly fine. But you could also just paste all the images here, and that's also perfectly fine. And you can see that for the labels directory, I did exactly the same. We have a directory which is called train, and within this directory is that we have all these different files. And for each one of these files, let me show you like this, it's going to be much better. For each one of these files, for each one of these txt files, we will have an image in the images directory, which is called exactly the same file name, but a different extension, right? So in this case, this one is called .txt and this one is called .jpg, but you can see that it's exactly the same file name. For example, the first image is called OA2 EA8F and so on, and that's exactly the same name as for the first image in the images directory, which is called OA2EA8 and so on. So basically, for absolutely every image in your images directory, you need to have an annotations file and a file in the labels directory, which is called exactly the same, but with a different extension. If your images are .gpg, your annotations files are .txt. So that's another thing which also defines the structure you need for your data, and that's pretty much all. So remember, you need to have two directories. One of them is called images, the other one is called labels. Within the images directory is where you're going to have all your images, and within your labels directory is where you will have all your annotations or your labels. And for absolutely every single image in your images directory, you will need to have a file in the labels directory which is called exactly the same but with a different extension. If your images are .jpg, your annotations file should be .txt, and the labels should be expressed in the YOLO format, which is as many rows as objects in that image, and every single one of these rows should have the same structure. You are going to have 5 terms. The first one of them is the class ID. In my case, I only have one class ID. I'm only detecting alpacas, so in my case this number will always be 0, but if you're detecting more than one class, then you will have different numbers. Then you have the position, the X and Y position of the center of the bounding box, and then you will have the width, and then you will have the height, and everything will be expressed in relative coordinates. So basically this is a structure you need for your data, and this is what this step is about. So that's pretty much all about converting the data or about formatting the data. And now let's move on to the training. Now is where we are going to take all this data and we are going to train our object detector using Yolov8. So now that we have taken the data into the format we need in order to train Yolov8, now comes the time for the training. Now it comes the time where we are going to take this custom dataset and we are going to train an object detector using Yolov8. So this is Yolov8 official repository, and one of the things I like the most about Yolov8 is that in order to train an object detector, we can do it either with Python, with a very few, only a few Python instructions, or we can also use a command line utility. Let me see if I find it over here. We can also execute a command like this in our terminal, something that looks like this, and that's pretty much all we need to do in order to train this object detector. That's something I really liked. That's something I'm definitely going to use in our projects from now on, because I think it's a very convenient and a very easy way to train an object detector or a machine learning model. So this is the first thing we should notice about Yolov8. There are two different ways in which we can train an object detector. We can either do it in Python, as we usually do, or we can run a command in our terminal. I'm going to show you both ways, so you're familiar with both ways. And also I mentioned that I am going to show you the entire process on a local environment in a PyCharm project, and I'm also going to show you this process in a Google Colab. So I know there are people who prefer to work in a local environment. I am one of those people, and I know that there are other people who prefer to work on a Google Colab. So depending on in which group are you, I am going to show you both ways to do it, so you can just choose the one you like the most. So let's start with it, and now let's go to PyCharm. This is a PyCharm project I created for this training, and this is the file we are going to edit in order to train this object detector. So the first thing I'm going to do is to just copy a few lines. I'm just going to copy everything, and I'm going to remove everything we don't need. Copy and paste. So we want to build a new model from scratch. So we are going to keep this sentence, and then we are going to train a model. So we are just going to remove everything but the first sentence. And that's all. Right? These are the two lines we need in order to train an object detector using Yolov8. Now we are going to do some adjustments. Obviously the first thing we need to do is to import Ultralytics, which is a library we need to use in order to import in order to train a Yolov8 model. And this is a Python library we need to install as we usually do. We go to our terminal and we do something like pip install and the library name. In my case, nothing is going to happen because I have already installed this library. But please remember to install it, and also please mind that when you are installing this library has many dependencies, so you are going to install many different Python packages. So It's going to take a lot of space, so definitely please be ready for that, because you need a lot of available space in order to install this library, and it's also going to take some time because you are installing many different packages. But anyway, let's continue. Please remember to install this library, and these are the 2 sentences we need in order to run this training from a Python script. So this sentence, we're just going to leave it as it is. This is where we are loading the specific Yolov8 architecture, the specific Yolov8 model we are going to use. You can see that we can choose from any of all of these different models. These are different versions, or these are different sizes for Yolov8. You can see we have nano, small, medium, large, or extra large. We are using the nano version, which is the smallest one, or is the lightest one. And this one we are going to use, the Yolov8 Nano, the Yolov8N. Then about the training, about this other sentence, we need to edit this file, right? We need a YAML file which is going to contain all the configuration for our training. So I have created this file, and I have named this file config.yaml. I'm not sure if this is the most appropriate name, but anyway, this is the name I have chosen for this file. So what I'm going to do is just edit this parameter, and I'm going to input config.yaml. This is where the config YAML is located. This is where the main.py is located. They are in the same directory, so if I do this, it's going to work just fine. And then let me show you the structure for this config.yaml. You can see that this is a very simple configuration file. We only have a few keys, which are path, train, val, and then names, right? Let's start with the names. Let's start with this. This is where you are going to set all your different classes, right? You are training an object detector, you are detecting many different categories, many different classes, and this is where you are going to input, is where you're going to type all of those different classes. In my case, I'm just detecting alpacas. That's the only class I am detecting. So I only have one class, is the number 0, and it's called alpaca. But if you are detecting additional objects, please remember to include all the list of all the objects you are detecting. Then about these 3 parameters, these 3 arguments, the path is the absolute path to your directory containing images and annotations. And please remember to include the absolute path. I ran some issues when I was trying to specify a relative path, relative from this directory, from my current directory where this project is created, to the directory where my data is located. When I was using a relative path, I had some issues, and then I noticed that there were other people having issues as well. I noticed that in the GitHub repository from Yolov8. I noticed this in the issues section. There were other people having issues when they were specifying a relative path. So the way I fix it, and it's a very good way to fix it, it's a very easy way to fix it, is just specifying an absolute path. Remember, this should be an absolute path. So this is the path to this directory, to the directory containing the images and the labels directories. So this is the path you need to specify here, and then you have to specify the relative path from this location to where your images are located, like the specific images are located, right? In my case, they are in images./train relative to this path. If I show you this location, which is my root directory, then if I go to images train, this is where my images are located, right? So that's exactly what I need to specify. And then you can see that this is the train data. This is the data the algorithm is going to use as training data. And then we have another keyword, which is val, right? The validation data set, in this case, we are going to specify the same data as we use for training. And the reason I'm doing this is because we want to keep things simple. In this tutorial, I'm just going to show you the entire process of how to train an object detector using Yolov8 on a custom dataset. I want to keep things simple, so I'm just going to use the same data. So that's pretty much all for this configuration file. Now going back to main, that's pretty much all we need in order to train an object detector using Yolov8 from Python. That's how simple it is. So now I'm going to execute this file, I'm going to change the number of epochs. I'm going to do this for only one epoch because the only thing I'm going to show you for now is how this runs. I'm going to show you the entire process. And once we notice how everything is working, once we notice everything is up and running, everything is working fine, we can just continue. But let's just do this process, let's just do this training for only one epoch so we can continue. You can see that now it's loading the data. It has already loaded the data. You can make use of all the different information, of all these different debugging information we can see here. You can see now we were loading 452 images and we were able to load all the images, right? 452 from 452. And if I scroll down, you can see that we have additional information, additional values, which are related to the training process. This is how the training process is going. Right? We are training this object detector, and this is additional information which we are given through this process. So for now, the only thing we have to do is only waiting. We have to wait until this process is completed. So I am going to stop this video now, and I'm going to fast forward this video until the end of this training, and let's see what happens. Okay, so the training is now completed, and you can see that we have an output which says results saved to runs detect train 39. So if I go to that directory, runs detect and train 39, you can see that we have many different files, and these are files which are related to how the training process was done, right? For example, if I show you these images, these are a few batches of images which were used in order to train this algorithm. You can see the name is train batch 0 and train batch 1, and I think we have a train batch 2. So we have a lot of different images of a lot of different alpacas of different images we use for training, and they were all put together, they were all concatenated into these huge images, so we can see exactly the images which were used for training and the annotation on top of them, right? The bounding boxes on top of them. And we also have similar images, but for the validation dataset, right? Remember, in this case, we are using the same data as validation as we use for training, so it's exactly the same data, it's not different data. But these were the labels in the validation dataset, which is the training dataset, and these were the prediction on these same images, right? You can see that we are not detecting anything. We don't have absolutely any prediction. We don't have absolutely any bounding box. This is because we are doing a very shallow training. We are doing a very dummy training. We are training this algorithm only for one epoch. This was only an example to show you the output, how it looks like, to show you the entire process, but this is not a real training. But nevertheless, these are some files I'm going to show you better when we are in the next step. For now, let me show you how the training is done from the command line, from the terminal, using the command I show you over here, using a command like this. And also let me show you how this training is done on a Google Colab. So going to the terminal, if we type something like this, YOLO detect train data, I have to specify the configuration file, which is config.yaml, and then model.yolov8 n.yaml, and then the number of epochs. This it's exactly the same as we did here, exactly the same. It's going to produce exactly the same output. I'm just going to change the number of epochs for 1, so we make it exactly the same. And let's see what happens. You can see that we have exactly the same output. We have loaded all the images, and now we are starting a new training process. And after this training process, we are going to have a new run, which we have already created a new directory, which is train 40. And this is where we are going to save all the information related to this training process. So I'm not going to do it because it's going to be exactly the same as the one we did before. But this is exactly how you should use the command line, or how you can use this utility in order to do this training from the terminal. You can see how simple it is. It's amazing how simple it is. It's just amazing. And now let me show you how everything is done from a Google Colab. So now let's go back to the browser so I can show you this notebook I created in order to train Yolov8 from a Google Colab. If you're not familiar with Google Colab, the way you can create a new notebook is going to go Google Drive. You can click New, More, and you select the option Google Collaboratory. This is going to create a new Google Colab notebook, and you can just use that notebook to train this object detector. Now let me show you this notebook, and you can see that it contains only 1, 2, 3, 4, 5 cells. This is how simple this will be. The first thing you need to do is to upload the data you are going to use in order to train this detector. It's going to be exactly the same data as we used before. So these are exactly the same directories, the images directory and the labels directory we used before. And then the first thing we need to do is to execute this cell, which mounts Google Drive into this instance of Google Colab. So the only thing I'm doing is just I just pressed enter into this cell, and this may take some time, but it's basically the only thing it does is to connect to Google Drive, so we can just access the data we have in Google Drive. So I'm going to select my account and then allow, and that's pretty much all. Then it all comes to where you have the data in your Google Drive, right? In the specific directory where you have uploaded the data. In my case, my data is located in this path, right? This is my home in Google Drive, and then this is the relative path to the location of where I have the data and where I have all the files related to this project. So remember to specify this root directory as the directory where you have uploaded your data, and that's pretty much all. And then I'm just going to execute this cell. So I save this variable. I'm going to execute this other cell, which is pip install ultralytics, the same command I run from the terminal in my local environment. Now I'm going to run it in Google Colab. Remember, you have to start this command by the exclamation point, which means you are running a command in the terminal where this process is being executed or where this notebook is being launched. So remember to include the exclamation point. Everything seems to be okay, everything seems to be ready, and now we can continue to the next cell, which is this one. You can see that we have done exactly the same structure. We have input exactly the same lines as in our local environment. If I show you this again, you can see we have imported ultralytics, then we have defined this YOLO object, and then we have called model.train, and this is exactly the same as we are doing here. Obviously, we are going to need another YAML file. We are going to need a YAML file in our Google Drive, and this is the file I have specified, which has it's like exactly the same configuration as in the YAML file I show you in my local environment. It's exactly the same idea. So this is exactly what you should do. Now you should specify an absolute path to your Google Drive directory. That's the only difference. So that's the only difference. And I see I have a very small mistake because I see I have data here, and here I have just uploaded images and labels in the directory, but they are not within another directory which is called data. So let me do something. I'm going to create a new directory which is called data, images, labels. I'm just going to put everything here. Right, so everything is consistent. So now everything is okay. Images, then train, and then the images are within this directory. So everything is okay. Now let's go back to the Google Colab. Every time you make an edit or every time you do something in Google Drive, it's always a good idea to restart your runtime. So that's what I'm going to do. I'm going to execute the commands again. I don't really need to pip install this library again because it's already installed into this environment. And then I'm going to execute this file. I think I have to do an additional edit, which is this file. Now it's called googlecolab.config, and that's pretty much all. I'm just going to run it for one epoch, so everything is exactly the same as we did in our local environment. And now let's see what happens. So you can see that we are doing exactly the same process. Everything looks pretty much the same as it did before. We are loading the data. We are just loading the models. Everything is going fine. And this is going to be pretty much the same process as before. You can see that now we are, it takes some additional time to load the data because now you have You are running this environment, you are running this notebook in a given environment, and you're taking the data from your Google Drive, so it takes some time. It's a slower process, but it's definitely the same idea. So the only thing we need to do now is just to wait until all this process to be completed, and that's pretty much all. I think it doesn't really make any sense to wait, because it's going to be exactly the same process as we did from our local environment. At the end of this execution, we are going to have all the results in a given directory, which is the directory of the notepad which is running this process. So at the end of this process, please remember to execute this command, which is going to take all the files you have defined in these runs directory, which contains all the runs you have made, all the results you have produced, and it's going to take all this directory into the directory you have chosen for your files and your data and your Google Colab and so on. Please remember to do this, because otherwise you would not be able to access this data. And this is the data which contains all the results and everything you have just trained. So this is how you can train Yolov8, an object detector using Yolov8 in a Google Colab, and you can see that the process is very straightforward and it's pretty much exactly the same process, exactly the same idea as we did in our local environment, and that's it. So that's how easy it is to train an object detector using Yolov8 once you have done everything we did with the data, right? Once you have collected the data, you have annotated the data, you have taken everything into the format Yolov8 needs in order to train an object detector. Once everything is completed, then running this process, running this training is super straightforward. So that's going to be all about this training process, and now let's continue with the testing. Now let's see how these models we have trained, how they performed, right? Let's move to the next step. And this is the last step in this process. This is where we are going to take the model we produced in the training step, and we're going to test how it performs. This is the last step in this process. This is how we are going to complete this training of an object detector using Yolov8. So once we have trained a model, we go to this directory. Remember to the directory I showed you before regarding the directory where all the information was saved, where all the information regarding this training process was saved. And obviously I'm not going to show you the training we just did, because it was like a very shallow training, like a very dummy training, but instead I'm going to show you the results from another training I did when I was preparing this video, where I conducted exactly the same process, but the training process was done for 100 epochs. So it was like a more deeper training, right? So let me show you all the files we have produced, so you know what are all the different tools you have in order to test the performance of the model you have trained. So basically you have a confusion matrix, which is going to give you a lot of information regarding how the different classes are predicted, or how all the different classes are confused, right? If you are familiar with how a confusion matrix looks like, or it should look like, then you will know how to read this information. Basically, this is going to give you information regarding how all the different classes were confused. In my case, I only have one class, which is alpaca, but you can see that this generates another category, which is like a default category, which is background, and we have some information here. It doesn't really say much. It says how these classes are confused, but given that this is an object detector, I think the most valuable information is in other metrics, in other outputs. So we are not really going to mind this confusion matrix. Then you have some plots, some curves. For example, this is the F1 confidence curve. We are not going to mind this plot either. Remember, we are just starting to train an object detector using Yolov8. The idea for this tutorial is to make it like a very introductory training, a very introductory process. So we are not going to mind in all these different plots we have over here, because it involves a lot of knowledge and a lot of expertise to extract all the information from these plots. And it's not really the idea for this tutorial. Let's do things differently. Let's focus on this plot, which is also available in the results which were saved into this directory. And you can see that we have many different plots. You can definitely go crazy analyzing all the information you have here, because you have 1, 2, 3, 4, 5, 10 different plots. You could knock yourself out analyzing and just extracting all the information from all these different plots. But again, the idea is to make it a very introductory video and a very introductory tutorial. So long story short, I'm just going to give you one tip of something, the one thing you should focus on these plots for now. If you're going to take something from this video, from this how to test the performance of a model you have just trained using Yolov8 to train an object detector, is this. Make sure your loss is going down, right? You have many plots. Some of them are related to the loss function, which are this one, and this one. This is for the training set, and these are related for the validation set. Make sure all of your losses are going down, right? This is like a very, I would say, a very simple way to analyze these functions or to analyze these plots. But that's, I will say that that's more powerful than it will appear. Make sure all your losses are going down, because given the loss function, we could have many different situations. We could have a loss function which is going down, which I will say it's a very good situation. We could have a loss function which started to go down and then just it looks something like a flat line. And if we are in something that looks like a flat line, it means that our training process has stuck. So it could be a good thing, because maybe the algorithm, the machine learning model already learned everything it had to learn about this data. So maybe a flat line is not really a bad thing. Maybe, I don't know, you will have to analyze other stuff. Or if you look at your loss function, you could also have a situation where your loss function is going up, right? That's the other situation. And if you, my friend, have a loss function which is going up, then you have a huge problem. Then something is obviously not right with your training. That's why I'm saying that analyzing your loss function, what happens with your loss, is going to give you a lot of information. Ideally, it should go down. If it's going down, then everything is going well, most likely. If it's something like a flat line, well, it could be a good thing or a bad thing. I don't know. We could be in different situations. But if it's going up, you have done something super wrong. I don't know what's going on in your code. I don't know what's going on in your training process, but something is obviously wrong, right? So that's like a very simple and a very naive way to analyze all this information, but trust me, that's going to give you a lot of information in order to start working on this, testing the performance of this model. But I will say that looking at the plots and analyzing all this information and so on, I will say that's more about research. But that's what people who do research like to do. And I'm more like a freelancer. I don't really do like research. So I'm going to show you another way to analyze this performance or this the model we have just trained, which from my perspective, it's a more it makes more sense to analyze it like this. And it involves to see how it performs with real data, right? How it performs with data you have used in order to make your inferences and to see what happened. So the first step in this more practical, more visual evaluation of this model, of how this model performs, is looking at these images. And remember that before, when we looked at these images, we had this one which was regarding the labels in the validation set. And then this other one, which were the predictions, were completely empty. Now you can see that the predictions we have produced, they are not completely empty, and we are detecting the position of our alpacas super accurately. We have some mistakes actually. For example, here we are detecting a person as an alpaca. Here we are detecting also a person as an alpaca, and we have some misdetections. For example, this should be an alpaca and it's not being detected. So we have some misdetections, but you can see that the results are pretty much okay, right? Everything looks pretty much okay. The same about here. If we go here, we are detecting pretty much everything. We have a misdetection here. We have an error over here because we are detecting an alpaca where there's actually nothing. So things are not perfect, but everything seems to be pretty much okay. That's the first way in which we are going to analyze the performance of this model, which is a lot, because this is like a very visual way to see how it performs. We are not looking at plots. We are not looking at metrics, right? We are looking at real examples and to see how this model performs on real data. Maybe I am biased to analyze things like this because I'm a freelancer, and the way it usually works when you are a freelancer is that if you are building this model to deliver this project for a client and you tell your client, oh yeah, the model was perfect, take a look at all these plots, take a look at all these metrics, everything was just amazing, and then your client tests the model and it doesn't work, the client will not care about all the pretty plots and so on, right? So that's why I don't really mind a lot about these plots. Maybe I am biased because I am a freelancer and that's how freelancing works. But I prefer to do like a more visual evaluation. So that's the first step we will do, and we can notice already we are having a better performance. We are having an okay performance. But this data we are currently looking at right now, remember the validation data was pretty much the same data we use as training, so this doesn't really say much. I'm going to show you how it performs on data which the algorithm have never seen, with completely and absolutely unseen data. And this is a very good practice if you want to test the performance of a model. So I have prepared a few videos. So let me show you these videos. They are basically, remember this is completely unseen data. And this is the first video. You can see that this is an alpaca, which is just being an alpaca, which is just walking around. It's doing its alpaca stuff. It's having an alpaca everyday life. It's just being an alpaca, right? It's walking around from one place to the other, doing nothing. No, it's doing its alpaca stuff, which is a lot. This is one of the videos I have prepared. This is another video, which is also an alpaca doing alpaca related stuff. So this is another video we are going to see. Remember, this is completely unseen data. And I also have another video over here. So I'm going to show you how this model performs on these three videos. I have made a script in Python which loads these videos and just calls the predict method from Yolov8. From Yolov8, we are loading the model we have trained, and we are applying all the predictions to this model, and we are seeing how it performs on these videos. So this is the first video I show you, and these are the detections we are getting. You can see we are getting an absolutely perfect detection. Remember, this is completely unseen data, and we are getting, I'm not going to say a 100% perfect detection because we are not, but I will say it's pretty good. I will say it's pretty good in order to start working on this training process. Yeah, I will say it's pretty good. So this is one of the examples. Then let me show you another example, which is this one. And this is the other video I show you. And you can see that we are also detecting exactly the position of the alpaca. In some cases, the text is going outside of the frame because we don't really have space, but everything seems to be okay in this video too. So we are detecting exactly the position of this alpaca. The bounding box in some cases is not really fit to the alpaca face, but yeah, but everything seems to be working fine. And then the other video I show you, you can see in this case the detection is a little broken. We have many misdetections, but now everything is much better. And yeah, in this case it's working better too. It's working well. I will say in these three examples, this one it's the one that's performing better. And then the other one, I really like how it performed too, in this case where the alpaca was like starting its alpaca journey. And yeah, we had like a very good detection and a very stable detection. Then it like breaks a little, but nevertheless, I would say it's okay. It's also detecting this alpaca over here. So I would say it's working pretty much okay. So this is pretty much how we are going to do the testing in this phase. Remember that if you want to test the performance of the model you have just trained using Yolov8, you will have a lot of information in this directory, which is created when you are training the model. At the end of your training process, you will have all of these files, and you will have a lot of information to knock yourself out to go crazy analyzing all these different plots and so on. or you can just keep it simple and just take a look at what happened with the training loss and the loss and the validation loss and so on, all the loss functions. Make sure they are going down. That's the very least thing you need to make sure of. And then you can just see how it performs with a few images or with a few videos. Take a look how it performs with unseen data, and you can make decisions from there. Maybe you can just use the model as it is, or you can just decide to train it again. In this case, if I analyze all this information, I see the loss functions are going down, and not only they are going down, but I notice that there's a lot of space to improve this training, to improve the performance, because we haven't reached that moment where everything just appears to be stuck, right? Like that flat line. We are very far away from there. So that's something I will do. I will do an even deeper training so we can just continue learning about this process. Also, I will change the validation data for something that's completely different from the training data, so we have more information. And that's pretty much what I will do in order to iterate and in order to make a better model and a more powerful model. Hey, my name is Felipe and welcome to my channel. In this video I'm going to show you how to make an image classifier using Yolov8 on your own custom data. I'm going to show you every single step of this process, from how to organize the data so it complies with Yolov8, how to do the training in your local computer, and also from a Google Colab, how to validate the performance of the model you train, and finally how to take the image classifier in order to make new predictions. I'm going to show you the entire process. This is going to be an amazing tutorial, and now let's get started. So on today's tutorial I'm going to show you how to train an image classifier using Yolov8 on your own custom dataset. So let's get started, and the first thing I'm going to do is to show you the data I am going to use in this tutorial, which is a weather related dataset. Let me show you the different categories we have, and let me show you all the different images, how they look like. We have 4 different categories and they are cloudy, rain, shine, and sunrise. Now let me show you each one of these categories. For example, the cloudy category, this is how the images look like. You can see that in each one of these images we have a sky which is completely cloudy, right? We have many different clouds for each one of these images. Now the sunrise category, it's basically many different pictures of sunrises. So this is how this category look like. And now for the shine category, we have a sky which is completely clear and with a super bright sun, right? You have the sun in each one of these images and it's super bright. And this is a rainy category, and you can see these are many different pictures of super rainy days. So this is basically the dataset I am going to use in this tutorial, but obviously you can apply absolutely everything I'm going to show you today to absolutely any type of dataset. You are going to be able to build any type of image classifier with everything I'm going to say in this tutorial. Now let me show you the structure you need for your data, because if you're going to train an image classifier or if you're going to use Yolov8, yes, the data is super important, but you also need to structure, to give like a format to all of your data so it complies with the way Yolov8 expects your data to be, right? Yolov8 requires your data to be in a given format, in a given structure. So I'm going to show you exactly how to structure your file system so everything looks the way it should to train an image classifier using Yolov8. So if I show you, I have a directory which is called weather dataset. This is going to be the root directory. You can call this directory whatever you want, but you need a directory which is going to be your root directory. And inside this directory you can see we have 2 different folders. One of them is called train and the other one is called val, and this is exactly where you're going to have your training dataset and your validation dataset, right? It's very important you name these directories exactly like this. One of them should be called train and the other one val. Now if I show you within the train directory, this is where we are going to have our 4 directories containing all the different images for all of our categories. Basically you need to have as many directories as categories you want to classify with your model. So in my case I want to classify an image into 4 different categories, and this is why I have 4 different directories, 4 different models. Each one of these directories is named as the category I want to classify my image images in, right? One of them is called cloudy, the other one is called rain, then shine, and then sunrise, and these are the categories I want to classify all my images. And then within these directories, these folders, is where I have all my data. Within cloudy is where I have all my data related to the cloudy category and so on, right? The same happens for the rain and the shine and the sunrise category. So this is basically the structure you need for your data, the structure you need for your file system in order to comply with what Yolov8 is expecting for your data. And then if I go to the val folder, you can see I have exactly the same structure. I have 4 different directories and they are named under the categories I want to classify all my images. And then if I open these directories, it's exactly the same. You can see that I only have different images for that specific category. Now this is very important because from now on everything is going to be super straightforward. If you have created this structure for your file system, if your data is exactly in the structure I show you, then it's going to be super simple to train an image classifier using Yolov8. So this is very important. Now I'm going to show you 3 different ways in which you can train an image classifier using Yolov8. So let's start with the first way, which is using a Python script. We are going to make a very simple script in Python in order to train this model, and let me show you how to do it. So let's go to PyCharm. This is a PyCharm project I created for today's tutorial, and the first thing you should do if you want to work with Yolov8 is to install a couple of dependencies, a couple of Python packages. These are 2 packages we are going to use in this tutorial. One of them is Ultralytics and the other one is NumPy. Ultralytics is very super important because this is exactly the library you need in order to import YOLO, in order to train this model using Yolov8. So you definitely need these 2 packages. Now, in order to install these packages, this is how we are going to do it. I'm going to show you a way to install these packages, which is going to work with whatever your OS, right? If you are a Linux user, or if you are a Windows user, or if you use Mac, it doesn't matter, it's going to work anyway. So you need to go to File, then Settings, and then you have to select Python interpreter, right? This is the Python interpreter we are going to use. You can see that I'm using Python 3.8, and then you need to click on plus, and this is where you're going to find, you're going to search for the packages you want to install. In my case, I'm going to search for Ultralytics, and the version I'm going to use, let me copy the version first. It's this one, so I'm just going to File, Setting, then Ultralytics again, and then the version is this one. Okay, and then I click on install package. In my case, I have already installed this dependency, so nothing is going to happen on my computer, but please remember to do it on your computer, because otherwise you will not be able to use, or you're not going to be able to do anything of what we are going to be doing today. Now let's see NumPy, what's exactly the version we are going to use. We're going to use 1.24.2. So File, Settings, plus NumPy 1.24.2. So everything is okay. Now install package. This is like everything is okay. NumPy has been installed successfully. So now we are ready to continue. Once you have installed these 2 dependencies, these 2 packages, now you're ready to continue, and now you're ready to install your own image classifier using Yolov8. So let's go to main. This is the file we are going to use in order to code everything we need in order to train this classifier. And let me show you exactly what's the code you need to type in order to do this training. I'm going to over here to the GitHub repository of Yolov8, and I'm going to select the classification section, right? I'm going for the classification, and then here I'm going to click on classification docs. This is going to open a new file, a new URL, a new website, a new page, and this is exactly all the information we need in order to train this image classifier. I'm just going to scroll down, and I'm going to the train section, and this is what we're going to do. I'm going to copy and paste this line, which is the one in the middle, the one that says load a pre-trained model recommended for training. I'm just going to copy, and then I'm going back to PyCharm, and I'm just going to paste it. Obviously, we need to import YOLO, otherwise this is not going to work. So I'm going to say from Ultralytics import YOLO. And that's pretty much all. You can see now we are creating our model, or we are creating the object we are going to use as our model. And then I'm just going to copy and paste this last line, which is model.train. I'm going to paste it here. And then I'm going to make a few edits. I'm going to leave like this value. I'm going to leave the image size in 64. But then for the number of epochs, I'm going to set it in 1. Right? Because the first thing we're going to do is we're going to do a very dummy training in order to make sure everything works as expected, in order to make sure everything works properly. And once we are completely and 100% sure everything is okay, we are going to move forward with a more deeper training and with a more real training, right? But for now, let's just do the training for one epoch and let's see how it goes. Then for data, this is where you're going to specify the absolute path to the data you are going to train this model with, right? In my case, it's going to be this weather dataset. So I'm just going to copy and paste the absolute path of this dataset, which is this. I'm going to copy this path and I'm going to paste it here, right? This is data I am going to use. Remember that you need to specify the absolute path to the root directory of your data. And remember, you need to structure your data into the exact format I already mentioned, right? Otherwise, this is not going to work. And that's everything we need in order to train this image classifier. So the only thing I'm going to do is to press play. I'm going to run this script. So let's see what happens. Remember, we are running this training, we are doing this process for only one epoch because we need to make sure everything works properly. And once everything is working properly, we are just going to edit this value and we're going to make this training for more epochs. But you can see everything seems to be working properly, so everything seems to be okay, and everything seems to be completed, and everything seems to be ready. So that's it. And you can see that the results have been saved here in runs, classified, train 12. So let me show you exactly where this directory, where this location is in my file system. If I go to the project, the PyCharm project I created into my file system, this is exactly the project I created. This is the file we are currently working in, the main.py file, and this is where my data is located. And this is where the runs directory, the runs folder will be located. This is where it will be created. You can see that within runs we have another directory which is called classify, and here is where you will have many folders for each one of your training processes. And you can see that in my case I have trained this classifier many different times while I was preparing this video. So there are many directories for me, but this is exactly the one which was just created, the train 12, right? Train 12. This is exactly the directory which was just created. And if I open this directory, you can see we have another directory, and then we have two files. I'm going to explain what exactly all these different files and all these different folders are, and exactly what's the information we have in all these files, but I'm going to do it later on this tutorial when we are validating this training process, right? For now, just remember all the results will be saved here, will be saved within this folder, within the runs folder, and then within classify, and then a new directory, a new folder will be created for the training process you have just executed, right? This is something you need to remember for now, but later on in this tutorial I'm going to show you exactly how you can validate the training using the information that's within this directory. But for now, let's continue. I'm going to show you now a different way in which you can train this image classifier using Yolov8. I'm going to show you how to do it using the command line, using this utility. And this is actually like a very straightforward way to do this training. Let me show you. You can see that we have 3 different examples. I'm just going to select this one. I'm going to copy and paste this instruction, this line, and I'm going to show you how I do it. I'm just going to paste it here, and you can see that we have many different parameters, right? In the first word is YOLO, this is the utility we are going to execute. Then classify, this is the task we are going to execute. We are going to train an image classifier, and then we are going to train it. So we have another keyword which is train, and then we have these arguments: data, model, and epochs, and also image size. I'm going to do exactly the same with image size. I'm just going to leave this value in 64, but then I'm going to edit all the other values. Or actually, I'm going to edit number of epochs, and I'm also going to edit data. For the number of epochs, let's do something similar. I'm just going to do it for one epoch, so we make sure everything runs smoothly and everything runs properly, and then we can do like a more serious training, a more real training for more epochs. This is exactly the model I'm going to use, so I'm not going to edit this keyword either, and then I'm going to edit this argument, and I'm just going to say this is the absolute path to my data. So this is going to be exactly the same as I have over here. Something like this. Okay, and that's pretty much all. The only thing I need to do now, I'm going to copy and paste this sentence, and I'm just going to the terminal, and I'm going to do something like this, right? I'm just copying. I have just copy and paste that sentence, and you can see that that's all we need to do in order to train this image classifier using Yolov8. You can see that the model, the training process has started, and everything is running super smoothly. So everything is going super well. That's all, right? That's a very quick way and a very straightforward way to do this training. You can see that the training has just been completed, and this is exactly where the results have been saved to runs classifier train 13. So everything is completed, everything is ready. You can see how simple, how fast it is to train an image classifier just by running this command. Now I'm going to show you another way to do this training, which is using a Google Colab. We are going to use a Jupyter notebook. We are going to use a notebook in a Google Colab in order to train this model. And this is also like a very good way to do it. So let me show you how to do it. So basically you need to go to Google Drive. You need to go to your Google Drive. You need to select New, then More, Google Collaboratory, and this is going to open a new notebook. This is going to open a new notebook in Google Colab, and this is exactly what you need to do in order to use this notebook to train Yolov8. Now I'm going to show you a notebook I have already created in order to train this model, which is this one. It's called train.ipymb. And obviously I'm going to give you exactly this notebook in the GitHub repository of today's video, of today's tutorial, so you can just use this notebook if you want. Now I'm going to show you all these different cells, everything that's already written on this notebook, so you understand how exactly to use it and how it works and what exactly you are doing at each step. So let's start with the first step. Another thing you need to do if you want to train this image classifier is to upload all the data with all the images and with all your categories into Google Drive, obviously. For example, in my case, this is where I have my weather dataset. You can see that this directory is exactly the same directory I have over here. Weather dataset. Within weather dataset, there are two directories which are train and ball. If I open this directory, you can see we also have train and ball. So this is exactly the same data as in my local computer. Now this is something very important, because remember to do it, because you need the data in your Google Drive in order to train this model using a Google Colab. This is a very important step. Please remember to upload your data into Google Drive. Now, once your data is in Google Drive, then you need to be able to access your data from the Google Colab. And in order to do that, you need to execute this cell. If I click enter, you can see that now I'm going to be asked if I want to connect Google Colab with Google Drive. And the only thing I need to do is to say I accept. There you can see that it's requesting for my permission. I say connect to Google Drive. And then I select my account, and then basically is to go scroll down to the bottom of this page and to click allow. And this is going to allow Google Colab to access all the data you have in your Google Drive. So this is a very important step. Now, something that's very important is that you need to be able to access your data, so you need to know where your data is located in the Google Drive, right? You need to know exactly what's the path, what's the location of your data in Google Drive. In my case, let me show you my Google Drive. You can see that my data is located into a directory. This is my root directory, which is my drive. Then I have another directory which is called Computer Vision Engineer. Then another directory which is Image Classification, Yolov8, and then data, and then this is where my weather dataset is located. In your case, it's going to be different. Obviously, it depends on where exactly you have uploaded your data. So something you may want to do is just to click this ls. You can say something like ls, And then you say something like content, my G drive, my drive, right? You execute this command, and if I execute this command, you're going to see a very, very long list of files, which are basically all the files which are in my root directory in Google Drive. And for example, this is where I have the directory which is called Computer Vision Engineer, and if I do ls, you're going to see all these different directories. If I say something like image classification, Yolov8, then this is data train.ipynb, which is exactly this notebook. And then if I say data, this is exactly where the weather dataset is located, right? So do something like that, because you definitely need to know what is the path of your data in Google Colab, right? You definitely need to do it in order to continue to the next step. This is very important, because if you haven't set your data properly, if your data location is not set properly, then Yolov8 will not be able to train your model. This is very, very important. So in my case, this is exactly where the data, the weather dataset is located, right? This is the path to the weather dataset. So this is the cell I am going to execute, that this is the value I'm going to save in this value in data directory, in data dir. Now I'm going to continue. Then we need to pip install Ultralytics, which is the library we need in order to train this model, in order to use Yolov8. Now the only thing you need to do is to execute this cell, and everything will run super smoothly. You can see that we have already completed this process. Now I'm going to continue, and the only thing we need to do now is to execute this cell. And you can see that the code we have in this cell is very, very similar to the code we had over here, right? Basically, we are running a Python script from a Google Colab. That's all we're doing. So you can see we are importing OS, and also we are importing the YOLO library. We are importing from Ultralytics, we are importing YOLO, and then we are doing exactly the same as we are doing before. And this is where we are using the data directory, the data dir variable we have defined over here, right? So this is why it's very, very important you set this variable properly. So the only thing I'm going to do exactly the same as before. I'm just going to do this training for only one epoch, so we make sure everything's okay. I'm going to press enter, and that should be it in order to do all this training. The first time you execute this training, it may take a little longer, because you are downloading all the weights and you are downloading the models and everything, but after that everything should be much quicker. Okay, so you can see that now the training process is in progress. Everything is going super well, and from now on the only thing we need to do is to edit the number of epochs, so we do like a more deeper training. But I will say everything is working super properly. So now let's move to the other cell, so I show you what exactly you need to do once everything is completed. Once everything is completed, the only thing you need to do is to run this cell. So you are going to copy all your results which were saved on this directory. You're going to copy everything on your Google Drive, right? Because remember, you are working on a Google Colab, you're working on an environment which is your Google Colab environment. If you don't do something like this, it's going to be super hard for you to get the data you have just trained, right? To get your results, to get your model, your weights. It's going to be super hard, because everything is located in your Google Colab environment. And long story short, it's going to be much simpler and much better if you just do something like this and you just copy everything, all the results which were saved in this directory, into your Google Drive. It's going to be much better, because it's going to be much easier to download the weights, to download the results, and so on. So now I'm just going to wait a couple of minutes so everything is completed over here, and then I can show you how to copy the results into your Google Drive. Okay, now the training process has been completed, and you can see that the results have been saved into runs, classify, train. So these have very similar output to the one we just noticed when we were training on our local environment. Now, the only thing we need to do is to copy everything into our Google Drive, so everything is much simpler if we want to download these results or to do whatever we want. So the only thing I'm going to do is to run this cell, and everything will be copied into this directory, which is the same directory where I have my data and where I have my Google Colab, right? Now you can see that everything has been copied already. This is the directory I have just copied. This is the time, this is the current time. So this is the result of the cell I have just executed. And if I go to runs, classify, train, you can see that these are all the results we have generated. This is the CSV file containing many different results, which I'm going to show you in a few minutes, and these are the weights and so on. So from now on, if we want to get this data or if we want to analyze this data, the only thing we need to do is to select runs, and then we just need to click download, and this is going to download all this directory into your local drive, right? You can see everything is being zipping and once everything is zipped, this directory will be downloaded into my local computer, and you can see that this directory has just been downloaded, so everything is working just fine. Now, this is pretty much all in order to show you 3 different ways in which you can train an image classifier using Yolov8. And now let's do the deeper training, right? I'm just going to take this script and I'm going to edit the number of epochs. So we do this training for something like 20 epochs. I have already been doing some tests, and 20 epochs is just enough for this dataset, for the dataset I am using in this tutorial. So 20 will be just fine. Now, the only thing we need to do is to click on run. I'm just going to run this script as it is, and everything will be exactly the same as before. Everything will be exactly the same, right? We just need to wait until this process is completed. We don't need to do anything from now on, but this process will be executed for 20 epochs. So the only thing I'm going to do is to wait until this process is completed, and once everything is completed, we are going to validate this training process. I'm going to show you how to analyze if all this process was done successfully or not, if you have successfully trained a good image classifier or not. So I'm just going to pause the recording here, and I'm going to fast forward until this is completed. Okay, so the training process has been completed, and now let me show you all the results which were saved here into runs, classify, and train 14. Now let me show you this directory, this folder in my local computer. If I go to runs, classify, and then train 14, this is where all the results have been saved, and this is everything we're going to analyze now. Now we're going to decide if the model we have trained is a good model or not. We are going to decide if this is a model we can use or not. So you can see that there are 2 files, arg.yaml, results.csv, and another directory called weights. Let's start by args.yaml. If I open this file, you can see that this is something like a config file, and this is exactly the entire configuration file which we have just used in order to train this model. This is very important because this is a super comprehensive list of all the hyperparameters we have used in order to train this model. And for example, the only parameters we have specified are image size, number of epochs, and then data, the location of the data we have just used. And you can see that we have a keyword which is data, then epochs, then image size, and then we have many other keywords as well. This is very important because these are absolutely all the keywords we have used. We have used all these default values which were set for all these different keywords, and this is important in case we want to train a new model and we want to make some changes into some of these hyperparameters. Now let me show you the other file, which is the results.csv file. I will say this is much more important. This is like the file containing all the information we need in order to decide if this is a good model or not. And you can see that we have many different rows, each row for one of our training epochs, right? We have trained this model for 20 epochs, and you can see that we have 20 rows for each one of these epochs. And for each one of these rows, we have all this different information, and we are going to focus on these 3 values, on the training loss, the accuracy, this is the accuracy on the validation set, and then also the validation loss, right? These are the 3 keywords in which we are going to focus on this tutorial in order to validate this model. And I'm going to give you like a very quick tip, like a very quick way in order to analyze this training process, which is make sure the training loss and the validation loss are going down through this training process, and also make sure the accuracy goes up. And I know you're thinking, hey, this is a very simple way to analyze this process, Felipe. Yeah, I agree with you. This is a very simple way, but at the same time, it's very robust. This is like a A very simple but at the same time very powerful way to decide if you have a good model or not. Now, we can analyze all these numbers, but I think it's going to be much better, and it's going to be much prettier if we make a plot with all these numbers, right? Because we have epochs in this column, in this coordinate, and we also have all these different values, and we can definitely plot these values across all these different epochs. So let me show you a Python file I have created, and this is exactly what this Python file does. This file is called plot metrics, and if I open this file, you can see that it basically we need to set a path to our results.csv file. In our case, I'm going to set it to train14, and you can see that this is runs classified train14 and then results.csv, and then this is only like some logic, some very simple logic to take all the data from this results.csv file and to do some plots with it, right? That's all we're doing. We're just taking the data and doing some plots, and this file will be available in the GitHub repository of this project, of this tutorial, so you can definitely take this file and you can just use it to plot your functions as well. All I'm going to do now is just press play, and you can see that if we wait only a few seconds, we get all these two plots, right? And this is all the information in our CSV file, right? Everything I show you over here, it's summarized on these two plots. So this is exactly what I mean with make sure your loss is going down. This is our loss in the training set and in the validation set. In the training set, we are plotting the loss in blue, and in the validation set is red. And you can see that in both cases the loss is going down, right? Which is exactly what we expect. It's exactly what we want. Now, this is a very simple way to analyze this process, but trust me, this is also a very powerful way, right? This is something that's very healthy. Something that looks like this is very healthy. And then for this other plot, which is how the validation accuracy evolves through this training process, you can see that the validation accuracy goes up when we increase the number of epochs, right? You can see that starting from the 10th epoch or so, everything starts to be like somehow idle, right? We are not really gaining a lot of accuracy from here, but we are not losing accuracy either, right? We are just in something like a plateau. And this is exactly how a validation accuracy plot should look like, right? We are starting from a very low value, and then we are just increasing our accuracy until we reach a very high value of accuracy, right? This is like a very healthy training process. Now, obviously, we could make this process even better if we just if we just change some of these parameters, and if we do like a more customized training, I'm sure we will be able to have a better model, right? Because remember, we are using all the default values. So as it usually goes, if we make like a more customized training and we have different, and we try different AP parameters and so on, we should be able to get like a better model. But obviously we are not going to do it in this tutorial, because I just want to show you like the end-to-end on how to train this image classifier. But remember, you could do it even better than this if you make like a more custom model. So this is pretty much all for analyzing these plots, which are the validation accuracy and the loss function in order to validate your training. And then it's like the this directory, which is the weights directory. You can see that this directory is called weights, and this is exactly where the models will be saved. This is very important because you have trained a model, and now obviously you want this model in order to use it in your images, in your data. And this is exactly where you're going to find this model. And you can see that you have two different files. One of them is called last.pt and the other one is called best.pt. Now let me explain exactly what these two files are and exactly what they mean. So remember how this training process works, right? Remember that you have a model, you have a deep learning model, which is comprised of many different weights. And the way it goes is that at the end of every epoch, right? At the end of the first epoch, of the second epoch, of the third epoch, and so on, you are updating the weights of your model. You are updating the weights of your architecture, of your deep learning model. So the way it works is that at the end of every epoch you have a model available which is a model you have trained so far with all the process you have followed so far. So last.pt means that you are taking the model which was the result of the last epoch of your training process, right? Remember, at the end of absolutely every single epoch, you have a model available, you have a model which you can definitely use if you want to in order to produce your inferences and so on. So last.pt only means that you are taking the last model, the model which was produced at the end of your training process, at the end of the last epoch in your training process. So at the end of the 20th epoch in our training process, we are producing this model which is last.pt. But you may wonder, hey Felipe, yeah, it's great because at the end of our training process, our accuracy is something like a 93%, right? A 93% it's a very good accuracy. But if we take the accuracy, if we take the model at the end of the 16th epoch, for example, our accuracy it's higher, it's a 94.9%. Maybe it makes more sense to take that model instead, right? Because we have an even better accuracy, we have an even higher accuracy. And if you ask me something like that, I would say, yeah, you're perfectly right. You're super right. That's a very valid argument. And that's exactly what the best.pt model is, right? We are saving the weights of the best model in our entire training process. So if we look at our data, the best model in our training process is this one, if I'm not mistaken, right? It's the model we produced at the end of the 16th epoch, and our accuracy or validation accuracy was 94.9%. So this is definitely higher than the accuracy we got at the end of this training process, which was a 93.5%. And if we will take the best model we have produced in the entire process, in the entire training process, then we will definitely need to take this model. So this is exactly what best.pt represents, is the best training, the best model you have trained in your training process. And if you ask me, what I usually do is taking the model which was produced at the end of this training process, right? What I usually do is taking the last.pt file, because I consider that this is a model we have produced at the end of the training process. In this model, we are summarizing much more information, right? Because we are considering much more data, we are considering much more everything. In all this training process, many things are going on, many things are going on. And remember, there's a lot of randomness in this training process. So me personally, I consider that if I take the model which was trained at the end of this process, is a much better option than if I choose another one. If I choose like the best model or the model which I got the highest accuracy, but it's not the last model. That's what I usually do. I usually take the last model which was produced at the end of the training process. But if you want to take the best model, if you want to take the best.pt, it also makes sense because you are taking the model which produced the highest accuracy, right? So you can do either one of them, and I think it's a very good option. That's why you have these two files, because you can use one of them or you can use the other one. And I will say that making like a very like the best decision on which model to use depends on many different variables, depends on many different things, depends on your data, depends on your problem, depends on your use case, depends on your training process, depends on many different things, which is the best option, right? So remember, you have these two models and it's all up to you, it's all up to your specific project, and it's all up to your preferences which model you want to use, right? If the best model which you have produced through the entire training process, or if you want to use the last model, the model which you have produced at the end of your training process. So now let's go back to PyCharm, because now it's time to make our inferences. Now it's time to predict new samples, right? We are going to input an image and we're going to use our image classifier in order to predict which category this image belongs to. So let me show you how to do it. I'm going to import from Ultralytics, import YOLO. And then let's go back to this page, because now we are going to move to the predict section. And the only thing I'm going to do is to copy this sentence Going to paste it here, and then I'm going to specify the path, the absolute path to the model which we have trained, right? We don't really need to make it like the absolute path. We can use the relative path. So I'm going to do something like this, right? Sorry, something like this. So this is the path to the model we have just trained, right? This is the last model which we produce at the end of this training process, and this is the model I'm going to use in order to show you how this works. And now let's copy this additional sentence, which is results equal model and the model path, the image path. Right? You can see that you can use an image in your local computer, in your file system, or you can also use something like an URL. For example, in this case, in this example, which is in the Yolov8 website, you can see that the example is using a URL, and this is also going to work. So in my case, I'm going to use an image in my local computer. I'm going to use one of the images I used for training because I only want to show you how this works, but obviously you can use whatever data, whatever image you want. So this is the image I am going to use. I'm just going to inference this image, right? Which is the first image in my sunrise category data. So this is going to be something like sunrise1.jpg. And this is pretty much all. So these are the results. The first thing I'm going to do is just trying to run this code, and let's see what happens. Everything should run smoothly, but this is where we're going to see if we have any error or something like that. We may need to wait a couple of seconds, and everything seems to be working fine because we didn't get any error. So what I'm going to do now is I'm going to print results because I want to show you a couple of things. So this is the entire information we are getting when we are printing results, right? You can see that this is a lot of information. We have these probabilities, which is the inferences we are making. This is exactly the result of applying our image classifier. And then we have a lot of information. Another object or another result which is very important is this one, which are the names of the categories we have just trained our image classifier on, right? You can see that this is cloudy, rain, shine, sunrise, and also you can see that we have different integer values for each one of these categories. So this is something like a dictionary, because we are going to have a result from applying our image classifier, and then with this result, which is going to be an integer, we are going to call this dictionary, we're going to call this object, because we want to know exactly what's the name of the category we have just inferenced, right? So this is how we're going to do it. I'm going to call another variable, which is going to be names, something like names dictionary, names dict, and this is results 0 because results is a list. In this case, we only want to access the first element because we are only predicting an individual image, so this is the element we want. And then we are going to call dot names, and that's pretty much all. Then I'm going to define another variable, which is props, and this is results 0.props. And this is the probability vector of all the different categories we are trying to classify, right? So we are going to have a length 4 array with the probabilities of the different classes we are classifying, right? So let me show you how props looks like. I'm going to print props, and I'm going to do something else. I'm going to say to list, so we make this object into a list. We are using YOLO, which is based on PyTorch. So if we don't do this, if we don't call this method, we will be working with a torch object, right, with a tensor. So we don't really want to do that. So that's why I'm doing this to list. Now I'm going to print props, so I show you how it looks like, and I show you how to continue from here. Okay, you can see that this is a result we got from printing props, and you can see that this is a list with 4 elements, 1, 2, 3, and 4, and each one of these elements are the probabilities of this image to be one of these categories, right? Let's print the names too, so we have all the information in our screen. I want to show you something, so I'm going to print, sorry, this wasn't names, this was names dict. And now let's wait a couple of seconds. I want to show you not only the probabilities but also the class names, so it's a little more clear what exactly I'm going to show you now. So this means that this number is the probability for this image to be cloudy, right? This other number is the probability for this image to be rain. This other number is the probability to be shine, and then this last number is the probability to be sunrise. And you can see by the values that we are definitely classifying this image as sunrise, right? Because this is almost a 1. This is almost like a super confident and absolutely confident classification. So this is exactly the category we are classifying for this image, and this is how to make sense of this information. So what I'm going to do now is to print names dict, and then I'm going to call mp.argument_argmax, and then I'm going to input the probability list I just showed you. And obviously I need to import numpy as mp, otherwise it's not going to work. And basically what we are doing here is that we are looking at this list, the one containing all of our probabilities. We are taking a look at the maximum number, which in this case is this one, and we are taking the index of this maximum number. So in this case, this is the first element, so this is the index 0, this is 1, this is 2, and this is 3, right? So from this from calling mp.argmax props, we are getting 3, and then we are calling the third element of the namesdict object. So we go here and we see that 3 belongs to the sunrise category. And if we look at this image again, we are going to see we are in fact plotting a sunrise. Let me show you. So everything seems to be working fine, and this is going to be all for today. This is exactly how you can train an image classifier using Yolov8 in your own custom data, and this is going to be all for this tutorial. So in my previous videos I showed you how to train an image classifier and an object detector using Yolov8. Now is the time for semantic segmentation. I'm going to show you the entire process of how to train a semantic segmentation algorithm using Yolov8, from how to annotate the data, how to train the model in your local environment and also from a Google Colab, and finally a super comprehensive guide on how to validate the model you trained. My name is Felipe, welcome to my channel, and now let's get started. So let's start with today's tutorial, and the first thing I'm going to do is to show you the data we are going to be using today. So this is the asset I have prepared for today's tutorial, and you can see that these are images of ducks. We are going to be using a duck dataset today, and this is exactly how the images look like. Now for each one of our images, for absolutely every single one of our images, we are going to have a binary mask. We are going to have an image, a binary image, where absolutely every single pixel is either white or black, and absolutely every single white pixel is the location of our objects. All the white pixels are the location of the objects we are interested in. In this case, the objects are our ducks. So let me show you an example so it's a little more clear what I mean regarding the white pixels are the location of our objects. So this is a random image in my dataset, this is a random image of a duck, and this exactly its binary mask. So take a look what happens when I align these two images and when I apply something like a transparency. You can see that the binary mask is giving us the exact location of the duck in this image. So this is exactly what it means that the white pixels are the location of our objects. So this is exactly the data I am going to be using in this tutorial, and now let me show you from where I have downloaded this dataset. This dataset I have found in the Open Images dataset version 7. Let me show you this dataset super quickly. This is an amazing dataset you can use for many different computer vision related tasks. For example, if I go to segmentation, you can see that we have many different categories. Now we are looking at a random category of fonts. This is, for example, a semantic segmentation dataset of fonts, and let me show you. If I go here and I scroll down, you can see that one of the categories is here, DAC. So this is, for example, the exact same data I am going to be using in this tutorial. This is the exact same DAC dataset I am going to be using in order to train a semantic segmentation algorithm using Yolov8. And obviously you could download the exact same data I am going to use in this tutorial. If you go to Open Images Dataset version 7, you can just download the exact same DAC dataset I am going to be using today, or you can also download another dataset of other categories. So this is about the data I am going to use in this project, and this is about where you can download the exact same data if you want to. Now let me show you a website you can use in order to annotate your data, because in my case I have downloaded a dataset which is already annotated, so I don't have to annotate absolutely any of my images. Absolutely all of my images already have its binary masks, right? I already have the masks for absolutely all the images in my dataset. But if you're building your dataset from scratch, chances are you will need to annotate your images. So let me give you this tool which is going to be super useful in case you need to annotate your data. It's called CBAT, and you can find it in cbat.ai, and this is a very popular computer vision annotation tool. I have used it I don't know how many times in my projects, and it's very popular and it's very useful. So I'm going to show you how to use this tool in order to annotate your images. So the first thing we need to do is to go to start using CBAT. This is going to ask you to either register if you don't have a user already, or to log in, right? I already have a user, so this is logged into my account. And now let me show you how I'm going to do in order to annotate a few images. Actually, I'm going to annotate only one image, because I am only going to show you how to use it in order to create a binary mask for your project. But I'm just going to do it with only one image, because it's, yeah, you only need to see the process, and that's going to be all. So I'm going to projects. I'm going to here to the plus button, create a new project. The name of this project will be DAC Semantic Semseg. This will be the name of my project, and it will contain only one label, which is DAC. So I'm going to press continue, and that's pretty much all. Submit and open. Now I'm going to create a task. This is already, yeah. Create new task. The task name will be doc task 01. It doesn't really matter the name, so I just selected a random name. Then I'm going to add an image. I'm just going to select this image. I'm just going to annotate one image, so this is going to be enough, and submit and open. So this is going to take a couple of seconds. This is where you need to select all of your images, all the images you want to annotate. But in my case, I'm only going to select one. So I'm going to press here in job. So this is going to open the annotation job, right? Now I'm going to show you how you can annotate this image, how you can create a binary mask for this image. You need to go here to draw new polygon, then shape. So I'm going to start over here. And this is pretty much all we need to do in order to create the semantic segmentation dataset for this image, right? In order to create the binary mask for this image. You can see that I'm just trying to follow the contour of this object. And you may notice that the contour I am following is not perfect. Obviously, this is not perfect, and it doesn't have to be perfect. If you're creating a dataset, if you are creating the mask of an image, if you are creating the mask of an object, then it definitely doesn't need to be pixel-wise perfect, right? You need to make a good mask, obviously, but something like this, as I am doing right now, will be more than enough. So this is a very time-consuming process, you can see, and this is why I have selected only one, because if I do many images, it's going to take me a lot of time, and it doesn't make any sense, because the idea is only for you to see how to annotate the images, right? So you can see that I'm following the contour. Okay, and this is an interesting part, because we have reached the DAC's hand or its leg or something like that, this part of the duck's body. And you can see that this is beneath the water, this is below the water, and this is where you're going to ask yourself, do you need to annotate this part or not? Do you need to annotate this part as if it's part of the duck or not? Because you could say, yeah, it's definitely part of this duck, but you are not really seeing a lot of this object, right? It's like part of the water as well. So this is where you're going to ask yourself if you need to annotate this part or not. And in my case, I'm going to annotate it, but it's like you can do either way. In all of those sections, in all of those parts where you're not 100% convinced, then that's like a discussion. You could do it, you could not do it, it's up to you. So annotating a few images is always a good practice because you are going to see many different situations, as I have just seen over here, right? Where I have just seen with this part of the duck, which now I am super curious what's the name. If you know what's the name of this part of the duck's body, please let me know in the comments below. I think it's called hand, right? Because it's something like a hand they have over there. But let me know if it has another name, and if you know it, please let me know in the comments below. Now let's continue. You can see I'm almost there. I have almost completed the mask of this duck. Now I only have to complete this peak or whatever it's called. It seems I don't really know much about duck's anatomy. I don't really know how the name of this part either. So anyway, I have already completed, and once I'm completed, I have to press Shift N, and that's going to be all. So this is the mask. This is the binary mask I have generated for this object, for this duck, and this is going to be pretty much all. What I have to do now is to click Save. You can see that this is definitely not a perfect mask. This is not a perfect, like pixel-wise perfect mask, because there are some parts of this duck which are not within the mask, but it doesn't matter. Make it as perfect as possible, but if it's not 100% perfect, it's not the end of the world, nothing happens. So I have already saved this image, and what I need to do now is to download this data so I can show you how to download the data you have just annotated in order to create your dataset. So this is what I'm going to do. I'm going to select this part, this option over here, and I'm going to export task dataset, and then I'm going to select this option, which is segmentation mask 1.1. I'm just going to select that option, and I'm going to click OK. So that's going to be all. We only need to wait a couple of minutes, and that's pretty much all. The data has been downloaded. Now I'm going to open this file, and basically the images you are interested in are going to be here, right? You can see in my case I only have one image, but this is where you're going to have many images. And please mind the color you will get all these images in, right? In my case I have downloaded this image in red. It doesn't really matter, just mind that you could have something different than white. But once you have all your images, what you need to do is to create a directory. I'm going to show you how I do it. I am going maybe here, and I'm going to create a very temporal directory, which I'm going to call TMP, and this is where I'm going to locate this image, right? And I'm going to create two directories. One of them is going to be masks, and then the other one is going to be called labels, and you're going to see why in only a minute. And this is where I'm going to locate the mask here. And then I am going to PyCharm, because I have created a script, a Python script, which is going to take care of a very important process. We have created masks, which are images, which are binary images, and that's perfect because that's exactly the information we need in order to train a semantic segmentation algorithm. But the way Yolov8 works, we need to convert this image, this binary image, into a different type of file. We are going to keep exactly the same information, but we are going to convert this image into another type of file. So let me show you how. This is a Python file I have created in order to take care of this process, and the only thing you need to do is to edit these fields. This is where you're going to put all the masks. This is a directory which is going to contain all the masks you have generated, and this is going to be the output directory. You can see that these two variables are already named properly in my case, because this is a TMP directory I have just created. This is where I have located the mask I have just generated with CPAT, and this is my output directory. So take a look what happens when I press play. So the script has just been executed, everything is okay. This is the mask I had input, and this is the file which was generated from this mask. And this looks super absolutely crazy, right? It's a lot of numbers, it's like a very crazy thing. Without going into the details, let's just say that this is exactly the same information we had here. This is exactly the same information we have here, but in a different format. Let's keep that idea, right? Exactly the same information in a different format, and that's exactly the format Yolov8 needs in order to train the semantic segmentation model. So this is exactly what you need to do. Once you have created all of your masks, you need to download these files into your computer, and then please execute this script so you can convert your images into a different type of files. And obviously this script will be available in the GitHub repository of today's tutorial. So that's pretty much all in order to create your annotations, and in order to download these annotations, and in order to format everything the way you should. Now let me show you the structure you need to format, the way you need to structure all of your file system so it complies with Yolov8. Remember, this is something we have already done in our previous tutorials regarding Yolov8. Once you have your data, you need to structure your data, you need to format your data, you need to structure your file system so Yolov8 finds absolutely where everything is located, right? You're going to locate your images in a given directory, you're going to locate your annotations, your labels in another directory, so everything is just the way Yolov8 expects it to be, right? So let me show you. I have a directory which is my root directory, which is called data. Within data, I have 3 directories, but this directory, the masks directory, is not really needed. It's just there because that's the way I got my masks, my data, but it's not really needed. And in order to show you this directory, which is the one containing all of my binary masks, in order to be more clear that this is not needed for this part of this process, what I'm going to do is I'm going to delete this directory, right? Now it's gone. Okay, now we only have 2 directories, and these are exactly the directories we need in this part of this process where we are creating all the structure for our data. So images, you can see that we have 2 directories. One of them is called images, the other one is called labels. Within images, we have 2 other directories. One of them is called train, and the other one is called val. And train is the directory where we are going to have all of our training data. This is where we are going to have all of our training images. These are all the images Yolov8 is going to use in order to train the model, in order to train the semantic segmentation model. Then val also contains images, and these are the images we are going to use in order to validate the model, right? So remember, you need to have 2 directories. One of them should be called train. It's very important, the name, it should be called train, and the other one should be called val. Now, going back, you can see that we have 2 directories. One of them is images, the other one is label. And if I go within labels, you can see that there are 2 other directories. Also, they are named train and val. And if I open these directories, these are the type of files I have generated with the exact same script I showed you a few minutes ago. So, within labels, we have 2 directories, train and val. And train are all the annotations we have generated from the training data, from the training masks, right? Long story short, we have our root directory. Within the root directory, we have 2 directories. One of them is called images, the other one is called labels. Within images, we have 2 directories, train and val. Within train and within val, it's all of our data, all of our images. And within labels, it's exactly the same structure. 2 directories, train and val, and within train and within val, it's where we locate all of our annotations. right? That's exactly the structure you need for your data. Please remember to structure your file system like this, otherwise you may have an issue when you are trying to train a semantic segmentation model using Yolov8. So that's pretty much all in order how to structure the data. And now let's move to the interesting part. Let's move to the most fun part, which is training the semantic segmentation model. Now, let's move to PyCharm and I will show you how to train it from your local environment. So let's continue. This is a PyCharm project I created for today's tutorial. Please remember to install these project requirements, otherwise you will not be able to use Yolov8. Now let's go to train.py. This is a Python script I created, and this is where we are going to do all the coding we need in order to train the semantic segmentation model using Yolov8. And now let's go back to the Yolov8 official repository, because let's see how exactly we can use this this model in order to train the semantic segmentation model. I'm going to the segmentation section and I'm going to click on segmentation docs. Now this is going to be very straightforward. I'm going to train, I'm going to copy this sentence, which is load a pre-trained model, and I'm going back to PyCharm. I'm just going to copy paste, and then I am going to, from Ultralytics, import YOLO. Then I'm also going to copy this sentence, which is the model.train. I'm going to change the number of epochs to something like 1, because remember, it's always very healthy, it's always a very good idea to do like a very dummy training, to train the model for only 1 epoch, to make sure everything is okay, to make sure everything runs smoothly, and then you do like a more deeper training. So I'm going to change the number of epochs, and then I'm also going to change the config file. I'm going to use this config file, which is a config file I have over here. And obviously you will find this config file in the repository of today's video. So long story short, you can see that you have many different keywords, but the only one that you need to edit is this one, right? This is the absolute path to your data. In my case, if I copy and paste this path over here, you can see that this is the directory which contains the images and the labels directories. So long story short, just remember to edit this path to the location of your data. Because if you have already structured everything in the way I mentioned, in the way I show you in this video, then everything else will be just fine, right? The train and the val keywords are very good as it is. I mean, you can just leave everything as it is, but please remember to edit this field, which is the location of your data. Now going back to train.py, this is pretty much all we need to do in order to train the semantic segmentation model. So I'm just going to press play and let's see what happens. And you can see everything is going well. We are training our model, but everything is taking forever. Everything is just going to take forever. Even though we are only training this model for only 1 epoch, everything is going to take a lot of time. So what I'm going to do instead is just press stop. I'm going to stop this training. Everything is going well. I'm not stopping this training because I had an error or something. No, everything is going well. But I am going to repeat exactly the same process from a Jupyter notebook in my Google Colab. Because if I use Google Colab, I'm going to have access to a free GPU and it's going to make the process much faster. So I am going to use a Google Colab in order to train this model, and I recommend you to use a Google Colab as well. So I'm going to show you how to do it from your Google Colab environment. Please remember to upload your data before doing anything in Google Colab. Please remember to upload your data, otherwise it's not going to work. For example, here you can see I have many directories. One of these directories is data, and within data you have labels and images, and these are exactly the same directories I have over here. So I have already uploaded my data into my Google Drive. Please remember to do it too, otherwise you will not be able to do everything we're going to do just now, right? So that's one of the things you need to upload, and then also remember to upload this config.yaml file, the same file I show you in my local computer. You also need this file here. The only thing you will need to edit is this path, because now you need to specify the path, the location of your data in Google Drive. So I'm going to show you exactly how to locate your data into your Google Drive, and now let's move to the Jupyter notebook. Obviously, I'm going to give you this notebook. This is going to be in the GitHub repository of today's tutorial, so you can just use this notebook. I'm just going to show you how to execute absolutely every single cell and how everything works, right? And exactly how everything, exactly what everything means, right? Exactly what are you doing in absolutely every single cell. So the first thing I'm doing is just connecting my Google Colab environment with Google Drive, because remember, we need to access data from Google Drive, so we definitely need to allow Google Colab to access Google Drive. So I'm just going to select my account, and then I scroll all the way down and press allow. That's going to be pretty much all. We need to wait a couple of seconds. And now let's continue. What I'm going to do now is to define this variable, which is data dir, and this is the location of my data in my Google Drive. Now, please mind this path, this location, because please mind the way this is structured, right? Please mind the first word is content, then G drive, then my drive, and then is my relative path to my data. So if you want to know exactly where you have uploaded your data, if you're not completely sure where you have uploaded your data, what you can do is to do an ls like I'm doing right now, and this is going to give you all the files you have in the root directory of your Google Drive. Then from there, just navigate until the directory where you have uploaded your data. In my case is my drive, computer vision engineer, image segmentation, Yolov8, and then data. That's exactly where my data is located in Google Drive. If I go to this directory, you can see that this is my drive, then you can see that this is my drive, then computer vision engineer, image segmentation, Yolov8, and then data. And this is exactly what I have over here. So once you have located your data, the only thing you need to do is to edit this cell and to press enter. So everything is ready. Now I'm going to install Ultralytics so I can use Yolov8 from the notebook. And this is going to take a few seconds, but this is going to be ready in no time. Or something you need to do from your Google Colab is to go to runtime and change runtime type. Just make sure it says GPU. Just make sure you are using a Google Colab with GPU, because if you are not using a Google Colab with GPU, everything is pretty much pointless, right? So just remember to check if you are using a Google Colab with GPU or not. Just do it before you start all this process, because otherwise you will need to run absolutely everything again. So let's continue. I have already installed Ultralytics, and now I am going to run this cell. And if you realize, this is exactly the same type of information, the same code I have over here in my local environment, right? I'm just defining a model, and then I am just training this model. So what I need to do now is just press enter, and also mind that I have specified the config file, right? The location of my config file. And now I'm going to run a full training, or actually I'm going to run a training for 10 epochs. So this is what I'm going to do. And this is also going to take some time, although we are going to use a GPU. This is going to take a few minutes as well. So what I'm going to do now is just, I'm going to wait until this is completed, and I'm going to pause my recording here, and I'm just going to fast forward this video until this process is completed. Okay, so the training process is now completed. We have trained this model and everything is just fine. And you can see that results have been saved here under runs, segment and train 2. So the only thing we need to do now is to get the results we got from this training. We need to get the weights, we need to get all the results, all the different metrics, all the different plots, because what we need to do now is to analyze this training process. We need to validate that everything is just fine, right? So what we are going to do now is to get all this information, and the easiest way to do it is just running this command. What we will do when running this command, we are going to copy all the content in this directory where the results have been saved under our Google Drive, right? Remember to edit this URL, remember to edit this path, this location, because you want to copy everything into a directory into your Google Drive. So just make sure everything is okay. okay, make sure this location makes sense, and you can just execute this cell and you're going to copy everything into your Google Drive. Now let me show you my Google Drive. I have already executed this cell, so everything is under my Google Drive. This is a runs directory which was created when I ran that cell, and under this other directory which is called segment, we have train2. So these are all of our results. These are the results we are now going to analyze. So what I'm going to do now is just to download this directory, and once we have this directory into our local computer, then we are going to take a look at all the plots, at all the metrics, and I'm going to tell you exactly what I usually do in order to validate this training process. So everything is now downloaded, everything is now completed, and let's take a look at these files. So what I'm going to do is I'm just going to copy everything into my desktop. I need to do some cleaning, by the way. So these are all the results we got from this training process. You can see that this is a lot of information. This is definitely a lot of information, right? We have many different files. We have many different everything. We have the weights over here. We have a lot of information. So let me tell you, let me give you my recommendation about how to do this evaluation, how to do this validation. From all these plots and from all of these results, I will recommend you to focus on two things. One of them is this plot, one of them is all of these metrics, and then I'm also going to show you how to take a look at these results, at these predictions from these images. But for now, let's start here. You can see that this is a lot of information. These are a lot of metrics, and you can definitely knock yourself out analyzing all the information you have here. You can definitely go crazy analyzing all of this information, all of these plots, but I'm going to show you like a very simple and a very straightforward way to do this analysis, to do this validation. This is something that I have already mentioned in my previous videos on Yolov8 on how to train a model and how to validate this model, which is take a look what happens with the loss function. Take a look what happens with your loss plots, with all the plots which are related to the loss function. And as this is a semantic segmentation type of algorithm, I will tell you, take a look what happens with this loss, with the segmentation loss. I will say, take a look what happens with the training loss and the validation loss. And long story short, just make sure the loss function goes down, right? If your loss function is going down, it's likely things are going well. It's not a guarantee. Maybe things are not really going that well and the model doesn't really perform that well. It may happen. But I will say that if the loss function is going down, it's a very good sign. If, at the contrary, your loss function is going up, I will say you have a very serious problem. I will say there is something which is seriously wrong with your training process, or with your data, or with your annotations, or with something. You have done something seriously wrong, or there's something seriously wrong with your data. But I'm talking about something amazingly wrong, seriously wrong, right? If your loss function is going up, I don't know what's going on, but something is going on. Do you see what I mean? So having a loss function which is going down, yeah, it's not a guarantee of success. I mean, it's not like it's a good model for sure. No, you may have a situation where you haven't trained a good model and your loss function is going down anyway. But I would say that it's a very good sign. At the very least, your training loss and your validation loss should go down, and I'm talking about a trend of going down, right? For example, here we have a few epochs in which the loss function is going up. That's okay, that's not a problem. We are looking for a trend. We should have a trend for the loss function to go down. And that's exactly what we have in this situation. So, long story short, that's my recommendation on how to do this validation, how to do this analysis on all the metrics we have over here. For now, focus on these two and make sure they are going down. And then, in order to continue with this process, with this validation, is that we are going to take a look at what happens with our predictions. How is this model performing with some data, with some predictions? And for this, we are going to take a look what happens with all of these images, right? You can see that these are some badges, and these are some of our labels, some of our annotations for all of these images, and then these are some of the predictions for these images, right? So we are going to take a look what happens here, and for example, I'm going to show you these results, the first image, and you can see that looking at this image, which again, these are not all predictions, but this is all data, this is all annotations, these are all labels. You can see that there are many missing annotations. For example, in this image, we only have one mask, we only have the mask for one of our dogs. We have 1, 2, 3, 4, 5 dogs, but only one of them is annotated. We have a similar behavior here, only one of the dogs is annotated. Here is something similar, only one of them is annotated. And the same happens for absolutely every single one of these images. So there are a lot of missing annotations in this data we are currently looking at. And if I look at the predictions, now these are the same images, but these are our predictions. We can see that nevertheless we had a lot of missing annotations. The predictions don't really look that bad, right? For example, in this case, we are detecting 1, 2, 3 of the 5 dogs. So we have an even better prediction that we had over here. I would say it's not a perfect detection, but I would say it's very good, right? It's like, it's not 100% accurate, but it's like very good. And I would say it's definitely better than the data we use to train this model. So that's what happens with the first image, and if I take a look at the other images, I can see a similar behavior, right? This is the data we use for training this algorithm, and this is the predictions we got for these images, and so on, right? It seems it's like this, exactly the same behavior, exactly the same situation for this image as well. So my conclusions by looking at these images, by looking at these predictions, is that the model is not perfect, but I would say performs very well, especially considering that the data we are using to train this model seems to be not perfect, seems to have a lot of missing detections, have a lot of missing elements, right? A lot of missing objects. So that's our conclusion, that's my conclusion by looking at these results, and that's another reason for which I don't recommend you to go crazy analyzing these plots. Because when you are analyzing these plots, remember, the only thing you're doing is that you are comparing your data, the data you are using in order to train this model, with your predictions, right? The only thing you're doing is you're comparing your data with your predictions, with the predictions you got with the model, right? So as the only thing you're doing is a comparison between these two things, then if you have many missing detections or many missing objects, or if you have many different errors in your data, in the data you're using to train the algorithm, then this comparison, it's a little meaningless, right? It doesn't really make a lot of sense, because if you're just comparing one thing against the other, but the thing you are comparing with, it has a lot of errors, it has a lot of missing objects and so on, maybe the comparison doesn't make a lot of sense whatsoever, right? That's why I also recommend you to not go crazy when you are analyzing these plots, because they are going to give you a lot of information, but you are going to have even more information when you are analyzing all of these results. And this is a very good example of what happens in real life when you are training a model in a real project. Because remember that building an entire dataset, a dataset which is 100% clean and absolutely 100% perfect, is very expensive. So this is a very good example of what happens in real life. Usually the data you're using to train the model, to train the algorithm, has a few errors. And sometimes there are many errors. So this is a very good example of how this validation process looks like with a data which is very similar to the data we have in real life, which in most cases is not perfect. My conclusion from this evaluation, for this validation, would be improving the data, taking a look what's going on with the data. And the next step would be to improve the data. And by looking at these results, one of the ways in which I could improve this data is by using the predictions I'm getting instead of the annotations I used to train this model. You see what I mean? If the predictions we are getting are even better than the annotations, maybe a next step would be to use these predictions in order to train a new model. Do you see what I mean? So, by analyzing all of these results, you are going to make decisions on how to move forward, on how to continue. And this is a very good example of how this process looks like in a real project. This is pretty much how it works, or how it looks like when you are working in a project, when you are working either in a company, or if you are a freelancer and you're delivering a project for a client. This is pretty much what happens, right? There are errors, things happen, and you need to make a decision given all the information you get with all this analysis. So that's going to be all in order to show you this very simple and very straightforward way in order to validate this training process and in order to make some conclusions regarding what's going on, right? And regarding to make some decisions in order how to move forward with this project or with this training process. And now let me show you something else, which is within this directory, the weights folder. This is where your weights will be located, right? Because if you are training a model, it's because you want to have a model in order to make predictions, in order to make inferences. And this is where your models will be located. This is where your models will be saved. And this is something I have already mentioned in one of my previous videos regarding Yolov8. Remember, you will have two models. One of them is called last.pt and the other one is best.pt. And the way it works is that, remember that when you are training a model, at the end of absolutely every single epoch, you are updating your weights, you are updating your model. So at the end of absolutely every single epoch, you already have a model which is available, which you can use it if you want to. So last.pt means that you are getting the last model, the model you got at the end of your training process. So in this case, I am training a network for 10 epochs, if I remember correctly. So this is the model we got at the end of the 10th epoch. And then best.pt means that you are getting the best model you train during the entire training process. If I show you the metrics again, let's see the metrics over here. You can see that we have many metrics which are related to the loss function, and then other metrics related to the accuracy on how this model is performing. And the way Yolov8 decides what's the best model in this case, which is a semantic segmentation type of problem, may be related to the loss function. Maybe it's taking the model in which you got the minimum loss, or it may be related to some of these plots, some of these performances which are related to the accuracy, to the performance. Maybe it's in the model for which you got the maximum precision, for example, or the maximum recall, or something like that. I'm not 100% sure, I should look at the documentation, but the way it usually goes is that last.pt is the last model you train, so it's at the end of your training process, and then best.pt is your best model, and this best model is decided under some criteria. So that's basically how it works, and what I usually do is taking last.pt, because I consider that last.pt is considering way more information, much more information, because we are taking much more data, we are taking much more everything, right? In all the training process, we are doing many different things. So if you take the last model, you are summarizing way more information. That's the way I see it. So usually I take the last model, usually I take last.pt. And that's pretty much all in order to show you this validation, how this validating this model looks like. And now let's move to the prediction. Let's see how we can use this model in order to make inferences, in order to make predictions. So let's see how we can do that. So let's go to PyCharm, let's go to the PyCharm project of today's tutorial, and this is a Python script I created in order to do these predictions. This Python file is called predict.py, and this is what we're going to do. I'm going to start importing from Ultralytics, import YOLO, and then I am going to define the model path, the model we are going to use. which in our case, let's use last.pt from these results from this directory. So I'm going to specify something like this, last.pt. And then let's define an image path. Let's define the image we are going to use in order to get our inferences. So the image will be located, this will be from the validation set. I'm just going to choose a random image, something like this one. So I am going to copy, paste, and I'm just going to paste it here. So this is the image we're going to use in order to test this model, in order to make our predictions. And now I'm going to import CV2 as well, because I'm going to read this image, and then I am going to get this image shape. So this will be something like this. This will be image, and then this is image.shape. Okay, and now the only thing we need to do is to get our model by doing something like YOLO and then model path. Okay, and then we are going to get the results by calling model of our image, right? And this is it. This is all we need to do in order to get our results, in order to get our inferences. But now let's do something else. I am going to iterate for result in results. And now let's take a look at this mask. Let's take a look at this prediction. So I'm going to iterate like this. For j mask in result.masks.data. And then I am going to say something like mask.numpy times 255, and this is our mask. And then I am going to resize it to the size of the image. So I'm going to input the mask, and then this will be, if I'm not mistaken, the order is this one, W and then H. So this is just the way it works. This is how we need to do it in order to get the prediction, and then in order to resize this prediction back to the size of the original image. So this is how it goes. And now the only thing we need to do is to call cv2imgwrite, and I'm going to save it. I'm going to save it here, and the name will be something like that. Let's call it output. This is only a test, so we don't really need to go crazy with the name. Let's call it output.png, and this will be our mask. And that's pretty much all. Let's see what happens. I'm going to press play. Let's see if everything is okay or if we have some error. Okay, so I did get an error, and yeah, this is because we need to enumerate. I forgot the enumerate. We are not using J actually, so I could just iterate in mask, but let's do it like this. Okay, everything ran smoothly, everything is okay, we didn't get any error. And now if I go back to this folder, to this directory, I can see this is the output we got. And now, in order to make absolutely 100% sure everything is okay, and this is a good mask, this is a good prediction, I'm going to make an overlay. I'm very excited. I don't know if you can tell, but I'm very excited. I'm just going to take this image over here, and then I'm going back here, and I'm going to take the original image. I'm going to do an overlay, so this will be raised to top. I'm going to align these two images together, and now let's make a transparency and let's see what happens. And you can see that we may not get like a 100% perfect mask, but it's pretty well. It's like a very, very good mask, especially considering the errors we detected in our data. So this is amazing. This is a very good detection. This is a very good result. So this is going to be all for this tutorial, and this is exactly how you can train a semantic segmentation model using Yolov8, and this is the entire process from how to annotate the data, how to train the model, and how to validate this model, and then how to make some predictions. So this is going to be all for today. So this is exactly what you will be able to do with today's tutorial. In this video we're going to work with pose detection using Yolov8, and I'm going to show you the entire process, from how to annotate your custom data for free using a computer vision annotation tool, how to prepare your data and your file system for training this pose detector, how to do the training in your local computer and also from a Google Colab, and how to do a super comprehensive evaluation of the model you trained. This is a much more complex problem. In my previous tutorials I show you how to train an image classifier using Yolov8, an object detector and an image segmentation model, and I will say that today's model, this keypoint detector, is much more complex than everything we did before. This is going to be an amazing tutorial. My name is Felipe, welcome to my channel, and now let's get started! And now let me show you the data we are going to use on this tutorial. We are going to use the AWA pose dataset, and let me show you exactly how this data looks like. So you can see that these are pictures of many different animals. Currently we are looking at antelopes. These are pictures of many different antelopes, and if I scroll down in this directory you are going to see I also have other animals. For example, here this is a bobcat, which is some sort of feline, some sort of cat. You can see that these are many different pictures of this animal, and if I scroll down a little more, you are going to see I also have buffaloes. So we also have pictures of buffaloes, and if I continue scrolling down you are going to see other pictures of other animals. For example, here I have a chihuahua, and you get the idea, right? We have pictures of many different animals, and all of these animals are quadrupeds because this is a quadruped keypoint detection dataset. Now let me show you the key points we are going to be detecting for each one of these animals, and you can see that these are many different key points. We have 39 key points in total, which is a lot, and we are detecting many different parts. For example, the nose, the eyes, the jaw, the tail, the legs, and also the ears, the horns, or whatever they're called, something like antler, it doesn't matter. We are detecting many different parts in these quadrupeds. So this is exactly the data we are going to be using today. I thought it was like a very cool dataset to use in pose detection, and now let's continue. So I'm going to show you how to do the entire process of training a pose detector using Yolov8 on your custom data. And in my case, the data I am going to use in this tutorial is already annotated, right? So I already have the annotations for this data, but if you are training this pose detector on your custom data, then most likely you will need to annotate the data yourself. So I'm going to show you how you can do that. I'm going to show you how to do the entire annotation process using CBAT, which is a very popular and a very awesome annotation tool for computer vision, and let me show you how to do it. So I'm going to cbat.ai, this is CBAT website, and I'm going to click here where it says start using CBAT. I'm going to show you how to create a project, how to create a task, and how to do all the annotation. Now I'm going to projects, and I'm going to click the plus button. I'm going to click here and create a new project, and this is going to be keypoint detection. This is going to be quadruped keypoint detection, which is exactly what we are going to be doing. Then add label, and I'm going to add quadruped, continue, and that's pretty much all. Submit and open. This is where you are going to add absolutely all the labels you have in your custom data. In my case, I only have one label, which is quadruped. Now let's continue. Now I'm going to create a task, create new task. The name of this task will be something like quadruped keypoint detection task 001. And I am going to add an image. I'm going to show you how to annotate this data with only one image. So I'm only going to select the first one, and then I'm going to click here and submit and continue. We have to wait a couple of minutes until the data is uploaded into the server, and once everything is completed we need to go to tasks. This is our project and this is the task we have just created, and I'm going to click in open. So this is pretty much all. Now I'm going to click here. This is going to open the task, and now we need to start our annotation process. So you need to click here where it says draw new points, and you need to select the number of points you are going to annotate. In my case, I'm going to annotate 39 points, but you need to select as many points as you are going to annotate. So now I'm going to click here in shape, and we need to start our annotation process. And something that's very, very, very important is that once you are annotating your data, you need to follow a given order, right? Once you are annotating all of your key points, you need to follow a given order with your key points. If I show you this image again, you can see that we have many different key points. We have the location of all the key points, but we don't really have any information regarding the order of these key points, right? This is very, very important because you cannot follow any random order. You need to follow a given order. You need to follow always the same order when you are annotating your data. So this is, for example, the order I am going to follow in this tutorial. You can see that the first key point I'm going to annotate is nose, then upper jaw, then lower jaw, mouth and right, and so on, right? You need to specify a given order for your data. Now I'm going to start this annotation process. So the first point is nose, which I'm going to set over here. Then the next one is upper jaw, which is going to be something like this, lower jaw, here, mouth and right, and this is the right from the perspective of this animal, right? So this is going to be here. Now mouth and left, and I don't really see the mouth and left, but I'm going to say it's around here. And I'm going to share a few comments later on this tutorial regarding the visibility of our key points, right? But for now, let's just continue. Now the next one is right eye, then right ear base, which is here, and then right ear end, which is over here. And I'm just going to continue with all of this list, and I'm going to resume this video when I'm completed. And these are the last two, body middle right, which is around here, and body middle left, which is around here. I don't see it, but it's around here. And you can see that this is all. These are my 39 key points. And now let me show you how you can export this data. But before, please remember to click save, otherwise it's always a good practice to click save. And not only you need the key points, but you also need to draw a bounding box around your object. This is very, very, very important, and I'm going to tell you why in a few minutes. But for now, remember that not only you need to annotate all of your key points, but you also need to draw a bounding box enclosing your object. So this is how I did it, and I'm going to click save again. This is the only image I'm going to annotate, but please remember to follow exactly the same process for all of your images. And now I'm going to tasks, and I'm going to show you how to export this data. You need to click here and export task dataset. Now you need to click here, and you can see that there are many different options in which you can export your data, and one of these options is Coco Keypoints 1.0. And this is very important because this is the exact format we need for our data. But I have tried to export the data into this format and it's not working. For some reason, it's not working. So I'm going to show you how to do it in CBAT for images 1.1. So click here, then OK. And then you just have to wait until everything is downloaded. Once everything is fully exported, you are going to see a file, a zip file, and within this file there will be another file called annotations.xml. Now let me open this file so I can show you how it looks like. You are going to see something like this, and at the bottom of this file you are going to see all of your annotations and all the images you have annotated and its annotations, right? So this is exactly the data you are going to generate using CBAT. Now, let me show you something else. I have created a Python project for today's tutorial, and let me show you a script I created in this Python project. And this script will be super useful because now that you have your annotations, now that you have your data, you need to convert your annotations into the exact format you need in order to use this post detector using Yolov8. So let me show you. Basically, you need to specify two variables. One of them is the location of your annotations.xml file, and you also need to specify the location of the directory where you want all your data to be saved, right? this script is going to parse through this XML file, is going to parse through this file, and it's going to extract all of your annotations, and it's going to save all of your annotations into the exact format you need in order to use Yolov8. So remember to specify these two paths, these two variables. One of them is the location of your XML file, and then where you want all of your newly created annotations to be saved, right? Where you want this output directory. So once you have set these two variables, the only thing you need to do is to run this script, and everything will run super smoothly. And remember, this script will be available in the GitHub repository of today's tutorial, so you can just go ahead and use it in order to convert all of your data into the format you need to use Yolov8. And now let's continue. Now I'm going to show you how you need to format, how you need to structure all of your data and your file system so it complies with Yolov8. So you can see that this is a directory which is called data, and this is the root directory where my data is located. You need a directory which will be the root directory where your data will be saved, where your data will be located. Within this root directory, you can see I have two folders. One of them is called images and the other one is called labels. It's very important that you name these two folders exactly like this. One of them should be called the images and the other one should be called labels. That's very important. Now, if I open one of these folders, you can see that I have two other folders. One of them is called train and the other one is called val. And it's very important that you name these directories exactly like this. One of them should be called train and the other one should be called val. So within train is where we will have all of our training data, all of your training images, right? You can see that these are all of our images, which are all the images we are going to use as training data. And within val, it's exactly the same. This is all the images we are going to use as a validation data, as our validation set, right? So within images, we have two directories. One of them is called train, the other one is called val, and within each one of these directories is where we have all of our data, all the data we are going to use in order to train this model, all the images we are going to use in order to train this model. But we also have additional data, which are the labels. Now let me show you how this other folder looks like. You can see that within labels, we also have two directories, which are also called train and val. And it's very important that you name these two directories exactly like this. One of them should be called train and the other one should be called val. And if I open the train directory, you can see that we have many txt files. And these are basically all of our labels for the training data, for all of our training images. If I go back to images train, you can see that for absolutely every single one of these images, we have an annotations file, right? For absolutely every single one of these images, we are going to have a txt file in this folder. And now let me show you for the other directory, for val, it's exactly the same, but for the validation data, for the validation images, right? So if I go back again, you can see that we have in the root directory, then images, labels. Within images, we have two directories, train and val, and within each one of these directories is where we have all of our images. And if we go to labels, we have also two directories, train and val, and within each one of these directories is where we have all of our labels. So this is exactly how you need to structure your file system. And now let me show you one of these annotations files, one of these labels files from the inside. Let me show you how they look like. So this is a random annotations file, this is a random txt file, and this is exactly how you need to put all the data inside these files. The annotations are specified in the Coco keypoint format, which is a very popular format for post detection. Now let me show you something. I'm going to do something which I'm obviously not going to save the changes, but it's going to be much better in order to show you how this annotations format works, right? How it looks like. So basically you can see that the first number is a 0 and this is our class ID. In my case, I only have one class, which is quadruped, so in my case this number will always be 0. But if you are making this project and you have many different classes, please remember that this number should be the class ID. So if you have different classes, you will have different numbers here. Now, the next four numbers are the bounding box of your object, right? Remember in CBAT, when we were annotating this data, I show you that not only we need to annotate the key points, but we also need to annotate the bounding box, right? And we annotated the bounding box. So these four elements, the four elements that come after the class ID are the bounding box, right? And this bounding box is specified in the YOLO format, which is the X and Y position of the center of the bounding box, and then the width and then the height of your bounding box. This is very important. So these two numbers are the XY position of the center of your bounding box, and then the width and the height. And then all of the other numbers, let me show you, you can see that we have these two numbers, which are a float, and then we have the number 2. And then we have exactly the same, two numbers and another 2. Then two numbers and another 2. Then we have 3 zeros, right? This looks like very, very strange. So now let's go back to my browser, because I want to show you this website, which is cocodataset.org, and this is where we are going to see exactly how this format works. So if I go back to key point detection, you can see that this is our explanation about how this format works. And if I read something which is here, you can see that absolutely every single key point will be specified as X and Y and a visibility flag B. So this means that for absolutely every single key point, we are going to have 3 values. We are going to have the X and Y position of that given key point, and we are also going to have another value, which is B, which is the visibility, right? Remember, we were going to talk about visibility later on this tutorial. This is later on this tutorial. So you can see that B has 3 possible values. B could be 0, and this means that the key point is not labeled, and in this case X and Y is going to be 0, 2, or B could be 1, and this means the key point is labeled but is not visible, or B could be 2, and this means the key point is labeled and it's also visible. And if we go back to the to this file, to the annotations, you can see that if we start over here, we have 2 numbers and then we have a 2, which means this key point is annotated, is labeled, and is also visible. Now if we continue, you can see that we have 2 numbers and then we have another 2, which means this other key point is also visible. Now if we continue, you can see exactly the same, 2 numbers and then a 2, and then if we continue, you can see that this we have 3 zeros. And we are in this situation, right? B equals 0, so we also have X and Y equals 0. And this means the key point is not labeled for this image, right? So long story short, after the bounding box, all the other numbers will be the key points. And you will have 2 values for the X and Y position, and then the third value will be the visibility of that given key point. Now, this is one of the possible formats in which you could format your data, and this is going to work just fine, but Yolov8 also supports a key point annotation with only 2 values, which means that if you don't have the visibility information for all of your key points, then it doesn't matter, because Yolov8 also supports you input your key points with only the X and Y coordinates. So long story short, we have the first number, which is the class ID, then we have 4 numbers, which are the bounding box, and then all of the other numbers are the key points. And you can specify your key points with 3 coordinates for every key point, which means we have the X and Y and also the visibility for that key point, or you can specify all of your key points with only 2 coordinates, which means it's the X and the Y coordinate of that given key point. So this is the way you need to label your data, this is the way you need to structure all of your annotations, and please remember to do it this way, otherwise it's not going to work. So now I'm just going to press Ctrl Z, because obviously I'm not going to save all of those changes, and that's pretty much all about how to format your data, how to format your file system, and how to put your data into the exact format you need in order to train this pose detector using Yolov8. And now let's go back to PyCharm. Let's go back to the PyCharm project I created for today's tutorial. And the first thing you need to do if you want to train this pose detector using Yolov8 is to install the project's requirements, which is basically Ultralytics. So please remember to install this package before starting with this training, because otherwise you will not be able to train a pose detector using Yolov8. So once you have installed Ultralytics, let's go back here to this file I created, which is train.py. I'm going to show you exactly what you need to code in this file in order to do your training. And in order to do so, let's go back here, which is Ultralytics website, and let's go to the pose page, and let's scroll down until this section over here. And the only thing I'm going to do is I'm going to copy and paste this line, and then I'm going to copy and paste this other line, right? So this is basically all we needed to do in order to train this model. And obviously I need to import from Ultralytics, import YOLO, and that's pretty much all. So this sentence over here, we can just leave it as it is. We can just leave it in this default value. But this one, I am going to make a couple of changes. I'm going to change the number of epochs. I'm going to train for only one epoch for now. And I'm also going to change the location of the configuration file. I'm going to use this file, which is config.yaml. And now I'm going to show you how this config.yaml looks like. So you can see that this is the configuration file I am going to use in this tutorial. We have three sections, one of them for data, then key points, and then classes. And let's go to the data section first. This is where you're going to specify all the locations to your data, to your images and your labels. So basically, you need to specify the root directory, the directory containing your data, which in my case is this one. Remember, the root directory, this is the directory which contains the images and the labels folders. And then you need to specify what's the location of the training images and the validation images. If you have made everything as I show you in this tutorial, as I showed you a few minutes ago, then you can just leave these two lines in these values, right? You can just leave everything as it is and everything will work just fine. The only thing you need to edit is the location of your root directory. Now let's go to this section over here, which is the key points. And we have two keywords, which are keypoint shape and flip index. And these two keywords are completely and absolutely new for us. This is something we haven't seen before in any of my previous tutorials about Yolov8. And you can see that in the case of keypoint shape, in my case it says 39.3. That's because I have 39 key points and I'm using the X, Y, and B format, right? I'm using 3 values for every single key point. So in my case, that's why I have a 3 over here. So this is how many key points you have in your data, and this is what format are you using. If you're using the X, Y format, in that case you will need to specify a 2, or if you're using the X, Y, and B format, and in that case you will need to set a 3, as I am doing over here. So that's for keypoint shape, and now let me explain what flip index is. And in order to further explain what this keyword means, I made a drawing over here where I'm going to show you exactly what it means. So you can see that this is a random image in my dataset, and actually this is the same image I used in order to show you how the annotation process looks like for this data. And you can see that this is a quadruped with all of its key points drawn on top, right? Now let me show you what happens if I flip this image horizontally, right? This is what I get. You can see that this is exactly the same image, but the only thing I did was to flip it horizontally. If I flip an image horizontally, now everything that used to be one of the sides, now it's the other side, right? Everything that used to be the right side, now it's the left side. And the other way around, everything that used to be the left side, now it's the right side. That's only what happens when you are flipping an image horizontally. But remember, we had many different key points, and many of these key points were related to one of the sides. For example, we had a key point for the right eye, we also had key points for the right ear, we had key points for the right legs, and the same situation for the left eye, the left ear, and the left legs, right? Many of our key points are related to one of the sides. If we flip the image horizontally, then we should be doing something with all of these key points which are related to one of the sides, right? When we are training a model using Yolov8, when we are training this type of model, one of the steps, one of the stages in this process, in the training process, is to do something which is called data augmentation. And this data augmentation means that we are taking the data and we are doing different transformations with this data. One of the transformations we are doing is related to flipping the image, right? So we are going to be flipping some of our images at random, and every time we are going to be doing an horizontal flip, we are going to have a situation like this. So now let's go back to this list, which is the list of all the different key points we have in this dataset, right? Remember, I already showed you this list when I was annotating this image, and remember, we start with the nose, then the upper jaw, then the lower jaw, and so on. So you can see that some of these key points are related, for example, in this case, to the right side. This is related to the left side. We have many key points over here which are related to the right side. Then we have many key points which are related to the left side. Then we have other key points which are not related to any of the sides. For example, neck base, neck end, throat, back. These are generic key points and they are not related to any of the sides. And we will need to do something with all the key points which are related to one of the sides. For example, these two, then all of these over here, and so on, right? You get the idea. That's exactly what we need to do, and that's exactly what this flip index keyword does, right? That's exactly the idea, the intuition behind this flip index. So let's go through this list. You can see that the first element is nose, and if we think about a nose, it's right in the middle, and nothing is going to happen when we flip the image, right? The nose will continue being the nose, will remain as the nose. And then the next element is the upper jaw. Exactly the same, nothing will happen with the upper jaw, will remain being the upper jaw after we flip the image horizontally. The same will happen with the lower jaw, but when we get to this element, this is the mouth end right, and we will have an issue here because the mouth end right, when we flip the image horizontally, will be the mouth end left. And the next element, which is mouth end left, when we flip the image horizontally, now it will be the mouth end right. You get the idea? These two values, these two key points will be flipped when we flip our image, right? And now let's take a look at this list we have over here, which is the value for flip index. And you can see that the first element is 0, then 1, then 2, then 4, 3, right? So we are flipping these two values, right? Instead of having a 3-4, which will be like the natural order, we have a 4-3. We are flipping these two values. And these are exactly the indexes of these two key points in the key point order. So, long story short, the only thing we will need to do in order to fix this issue we will have when we are flipping our images horizontally, the only thing we will need to do is going through all of our key points, and all of the key points which are related to the right side, we need to flip them in order to make them the left side, right? We only need to flip the right and the left side. That's the only thing we need to do. And that's what we need to specify here in this list. This is how the flipping will be done. So please be super careful with this list, and this, remember, means how your indexes will be flipped when the image is flipped horizontally. Now let's move to this section, and these are all of your names of all of your objects. In my case, I only have one object, which is quadruped. So in my case, this is very simple, but please remember to specify all the names and all the class IDs for absolutely all of your names. In my case, I only have one class ID, which is 0 and means quadruped. So that's pretty much all for the config.yaml, and now let's go back to train.py and let's continue. So once you have specified this configuration file and you have specified everything we have over here, the only thing you need to do is to execute this script, and that's all. That's how easy it is to train this model. But I'm going to stop this training because otherwise it's going to take a lot of time. If I train this model locally, it's going to take a lot of time. I have been doing some tests already, and yeah, it's going to take forever if I do it locally. But this is exactly the process you should follow if you want to train this model in your local environment. But I mentioned that I'm also going to show you how to train it in a Google Colab. So now let's go to my browser and let's see exactly how we can do this training from a Google Colab. The first thing you will need to do is go into your Google Drive and you will need to upload absolutely all of your data, obviously, because otherwise you will not be able to train this model from your Google Drive. And also you will need to upload your config.yam file. And everything will be just exactly the same as the file I show you in my local computer, but you will need to edit this field, which is the path, right? You can see this path over here. You will need to edit this with the path to your data in Google Drive. This is very important, and otherwise nothing is going to work. So please remember, you need to edit this path, and I'm going to show you exactly how to know what's the location of your data in your Google Drive. Now let's go back to this Google Colab. This is the Google Colab I created for this tutorial, for this training, and obviously you will be able to find this notebook in the GitHub repository of today's tutorial. So for now, just follow along. You can see that we have only a few cells, and the only thing I'm going to do is to execute these cells one by one. So I'm going to start with the first one, which is connecting my Google Colab environment with Google Drive. And now the only thing I have to do is to select my account. Then I scroll all the way down and I click allow, and that's basically all we need to do in order to connect our Google Colab with Google Drive. So this way Google Colab will be able to access the data you have in your Google Drive. We have to wait a few seconds, and that's pretty much all. You can see that everything has been mounted here in Content G Drive. And now the next step is to install Ultralytics, right? Because remember, we are going to use Ultralytics, which is the Python package we need to use in order to use Yolov8. And the only thing we need to do is to execute this cell, and everything is now completed. Now, in order to continue with the next two cells, you need to know where your data is located in your Google Drive. The only thing I'm going to do is to execute this cell, and this is going to list absolutely all the files in my local, in my Google Drive and in my root directory, right? You can see that these are many files, and from here the only thing I will need to do is to find where my data is located. In my case, it's located in this folder. If I do ls again, this is the content of this folder, so the only thing I need to do is to locate this directory. And then that's it, right? This is the content of this directory, which is where my data is located. So the only thing I need to do is something like this. And that's the content of my data directory, which contains the two folders, images and labels. Now that you know where your data is located in your Google Drive, now you can just copy and paste this path in your config file, right? Now that you know exactly where your data is located, you can just come here and you can edit this field, and you can just put wherever your data is located. And then you need to specify the location of your config.yaml file. And once you set this location over here, you are all set, and the only thing you need to do is to click enter, right? You need to execute this cell, and that's going to be pretty much all. Now everything is being executed. This is going to take some time. The first thing it's going to do is to download all the weights into this Google Colab environment, and that's pretty much all. It's going to get all the data, and then it's going to do the training. Okay, now the training process has been completed, and you can see that the results have been saved here in runs post train 4. So I'm going to show you how to execute this cell. So we copy the entire content of the runs directory into your Google Drive, right? Remember that the idea of this training process is to download the results, to download the weights, to download the entire results which have been saved here. And the way to do it, or one of the ways to do it, I would say the easiest way to do it, is to copy everything into Google Drive and then just download everything from Google Drive. So this is the simplest way to do it. And please remember to edit this path to the path where you want everything to be copied when you execute this cell. So let me show you. If I go back to my Google Drive, you can see this is a runs directory which was just generated, and within this directory is where we have this train 4, which is the result of the training process we have just executed. So everything seems to be okay, and what we will need to do now is to download this directory into our local computer. Now, remember, this was a very dummy training. This is a training we did for only one epoch. Obviously, you will need to do like a deeper training if you really want to train your pose detector on your data. One epoch, it's very unlikely to be sufficient. You will need to do like a deeper training. In my case, I have already trained the model with my data, and I did it for 100 epochs, right? I did it before starting this tutorial, so everything is already trained and we can just analyze the results. So now let's move to my local computer so I can show you exactly how to validate the model I trained using Yolov8. And you can see that these are many different plots, many different functions. We are plotting a lot of information, but we're going to focus in the loss function, and specifically we are going to focus in this loss, which is the loss function related to the pose. So we are going to focus on the pose loss related to the training set and the pose loss in the validation set. And if we look at the training set, you can see that the loss is going down. But not only is going down, but I will say that's going to continue going down for even more epochs, right? You can see that the trend is that it's going down and it's going to keep going down for more iterations, for more epochs. We haven't reached a plateau, and I will say that we are very far away of any plateau, right? So this is a very good sign, and it means the training process is going super well, and it means that the model has extra capacity, it has more capacity, so we could continue training this model and it will continue learning more about this data. That's what I take by looking at this pose loss in the training set. And if we look at exactly the same function but in the validation set, we can see that it's going down, so that's a good thing, but I have the impression that it's starting to be something like a plateau, right? It's not very clear because it's happening right in the end of this training process, but you can see that it somehow seems like this is going to be a plateau from now on, right? At the very least, we can see that it's going down there. That's absolutely and 100% clear, and then it's unclear what will happen from now on, or what would have happened if I would have trained this model for more epochs. But it seems we may have reached a plateau, and that's something we need to keep in mind in this validation process. But now let's take a look at exactly how it's performing with some images. So the way I'm going to do it is like this. I am going to open this image, which is one of the batches in the validation set, and these are all labels, right? These are not all predictions, but these are the labels, the annotations. Now I'm going to keep this open, and I'm going to open exactly the same batch, but or predictions, right? This is going to be a very good way to analyze the results, because now we have a lot of images and we need to make more conclusions. We need to take a look at more samples. We need to, this is a much more complex problem. In my previous tutorials, I show you how to train an image classifier using Yolov8, an object detector, and an image segmentation model. And I will say that today's model, this keypoint detector, is much more complex than everything we did before. So this validation process will be more complex as well. Now, if you look at all of these images, I'm going to focus on only one of them. I'm going to focus on this dog, on this Dalmatian, and I'm going to show you exactly what's going on here. Let's focus on this animal first, and you can see that basically these are all of our key points. These are our ground truth. These are all of our annotations, and these are all of our predictions. And you can see that it looks pretty well. It looks very well. I will say that if we look at all of these key points which are around the face, I will say they are perfect. I would say they are very good. And then if we look at these key points over here, you can see that it's very good as well. If we look at these 3 key points, it's also very good. These 2 key points over here as well, it's very good too. And then if we look at the legs, I can see something is going on here because I don't really see these 2 key points, so we are not detecting the legs. And if I look at the legs entirely, I will say something is going on because I don't really see, I think we have an issue in the legs. And also you can see that this key point, which is at the end of the tail, we are not detecting this key point either. So we have some issues. We have an issue in the tail and we have an issue around the legs, but everything else I will say that is pretty good. I don't know what you think, but I think it's pretty good. So this is one of the examples, and now let me show you another one, which is in another batch. Again, these are the annotations and these are the predictions. So let me show you what happens in this rhinoceros. Let me show you what happens. These are our annotations and these are our predictions. And you can see that we have a similar situation. Around the face, I would say everything is just okay. We have like a very good detection. Then over here, we have very good detection too. These 3 points are very well detected. Then over here, everything is okay. And then we also have an issue around the legs, right? We are not detecting all the key points in the legs properly. The same happens over here with this other leg, and the same happens in the tail, in this key point, which is the end tail. And then everything else seems to be working super properly. We are detecting all the key points, but we have an issue around the legs and around the tail. And now let me show you other examples. For example, this one over here. You can see that in this case we have the animal in a different posture, so it's a little more challenging for our model. And you can see that in this case we are detecting the face very well. Actually, we're not detecting this eye, but other than that, all of the other key points around the face are very well detected. And you can see these 3 key points over here. Everything is okay. This one is okay. This one too. And then you can see that we have all key points which are also very well detected, but we have an issue again around the legs, right? And that's pretty much what I noticed by looking at many of these examples, right? In many of these situations, we have many different situations because there are different animals, they are in different postures, they are in different everything. So we are going to notice different situations. But after inspecting a few of these images, I had the impression that the model is performing very well, but we may have an issue around the legs and around the tail. That was my impression by analyzing many of these pictures. So by combining this information, all the information we got by analyzing these images, all the key points, how they were detected and so on, and also combining everything with the loss function, with this plot regarding the loss function in the training set and in the validation set, my conclusions from here will be to make a deeper training, to train this model for even more epochs, and I am curious to see what will happen in that situation, because if I look at the training loss, I really like what I see. I think this model have way more capacity. I think we could train for, I don't know, 50 more epochs, 100 more epochs, and I think we will be in a very good situation. The training loss will continue to go down, and it will continue to go down in this way, right? It seems we are very far away from the plateau, but if I look at the validation loss, I'm not completely and absolutely sure what happened from now on. So what I will do now in order to improve these results, or in order to try to improve these results, will be to continue training for more epochs, and I will see what happens next. I will see what happens with this loss, and then I will see what happens by analyzing these images again, right? That will be my next step by analyzing all this information. So this is a very good example of how to analyze your model, how to analyze your data and your plots and so on in a more complex example as this one, because remember that now we are trying to detect, now we are trying to learn something that's way more complex as we did in our previous tutorials. Now we are not trying to learn like a bounding box or a mask, but we are trying to learn the entire structure of a quadruped. So that's, trust me, it's way more complex than everything we have made so far. So this is a very good example of how to validate a model when the problem is a little more complex. Take a look at the loss function, take a look what's going on, take a look in the training set and in the validation set, and also take a look at some examples, and then just make some conclusions. In my case, what I will do is to train for more epochs. And also, please remember that we are always using the default values of this training, right? We are training this model using all the default values. The only values we are specifying are the image size and the number of epochs, and that's it. And if I show you the entire configuration file we are using, is this one, and you can see that we have many hyperparameters. So another next step, in case a deeper training is not enough, another next step will be to play around with the different hyperparameters and to find another combination of hyperparameters which will be better for our use case. That's very important, because if you are approaching a more complex problem like this one, like the one I am doing right now, I will say that it's not very realistic to expect everything goes super well from the first attempt by using all the default values, right? I will say if the problem you are trying to solve is much more complex, then most likely you will need to play around with the different hyperparameters, and you will need to find a combination of hyperparameters that suits well with your problem, with your project. So that's what I can say about this validation process. And now let me show you something else, which is where the weights are located. Within this folder, you will see another folder which is called weights, and within weights you are going to see two files which are best.pt and last.pt. These are the models you generated with this training process, and this is something that I have already mentioned in my previous tutorials, but I'm going to say it again. Last.pt is the model you trained at the end of your training process, and best.pt means that this is the best model you trained in the entire training process. So you have these two models and you can just choose the one you like the most, and what I usually do is take in last.pt. I consider that this is a much more robust model, so this is the one I usually consider when I'm making my predictions. And that's pretty much all I can say about this validation, about validating this model. And now it's time to make our predictions. So let's get back to PyCharm, and let me show you this file, which is called inference.py. This is the file we are going to use in order to make predictions with the model we just trained. So let me show you how to do it. I'm going to start importing from Ultralytics, import YOLO. Ultralytics, import YOLO. And then I'm going to define my model path. I am going to specify the location of the model we just trained, right? Which is this one. In my case, this is the location of my model. I'm going to select last.pt, and I'm also going to set the path to an image. I'm going to use in order to show you how to make predictions. My image will be located in samples wolf.jpg. Let me show you super quickly the image I'm going to use in order to show you how to make predictions with Yolov8. Let's go to samples, and this is exactly the image I am going to use. You can see that this is the image of a wolf, which is obviously a quadruped, so it's going to be an amazing image in order to show you how to use this model. Now let's get back to PyCharm, and let's do something like this. I'm going to define my model like YOLO model path, and then we're going to say something like results equal to model image path. And I'm going to select the first element, because as we are predicting only one image, the first element will be just fine. And then it's just about iterating for result in results, and this will be something like for keypoint in result keypoints dot to list. There. And for now, the only thing I'm going to do is to print keypoint, so we make sure everything is okay, and let's see what happens. Okay, it seems I have an error, and I think I know what's the error. To list goes with without the underscore. So let's see now. Okay, now everything seems to be okay, and what I'm going to do now is I'm going to import cv2, because I am going to read the image and I'm going to plot all the key points on top of this image, right? That's going to be a very good way to show you how to predict all these key points. So cv2 in read image path. This is going to be image, and now I'm going to call cv2.putText maybe it's a very good idea to put the text of each one of these key points, to put the key point number on top of each one of these key points. So this is going to be image. Then the key point number will be, let's do it like this, key point index, key point in enumerate, okay, and then string key point index. Okay, now the location, and remember, this is how my key points look like. We have 3 values, and the values we care about in this moment are these 2, because these are the XY position of the key point. So I'm just going to do something like int key point 0 and int key point 1. Okay, now I have to select the font, which I'm going to set in this one, font Hershey Simplex. Then the font size, which I'm going to set in 1 for now. Then the color. Something is not right. Let me see. I think I'm not closing these brackets. I think that's reason. 1, 2. Okay, there. Let's see now. Everything's okay. 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 Now the color, which I'm going to set in green. So this is something like this. And then the text width, which I'm going to set in 2. And this is going to be all for now. Now let's see how it looks like, right? I'm going to call cv2 imshow image and my image. Then cv2 weight key 0. Okay, and that's pretty much all. What we are doing here is plotting the image and drawing all the key points on top of this image with the key point number on each key point, right? So it's going to be easier to know exactly what we are detecting in the entire image. And this is the result. Everything looks pretty well, but I'm going to do something so I can improve the visualization. I am going to make the font size equal to 0.5. And I'm going to press play again. Okay, now the visualization is a little better, and you can see that everything looks pretty well, right? We are plotting all the key points on top of our image, and this is exactly how you can make predictions using Yolov8. So the last thing I'm going to show you is to open this file, the class names, and let's take a look at exactly what we are detecting, right? So you can see here, 0, we have the nose, then upper jaw, lower jaw, mouth end right, mouth end left, and so on, right? You can see that, for example, 21, we are somewhere around here, which is back middle, it makes sense. Then 37, we are around here, body middle right, and then 36, belly bottom. So everything looks pretty well, and you can see that we are still getting the issues we noticed in the other pictures, which is the legs are not very well detected and the end tail is not very well detected either. But everything else seems pretty well. So this is going to be all for this tutorial on Yolov8. My name is Felipe, I'm a computer vision engineer, and this is exactly the type of videos and the type of tutorials I make in this channel. If you enjoyed this video, I invite you to click the like button, and I also invite you to take a look at these 2 videos over there. This is going to be all for today, and see you on my next video.